Hello guys, welcome to this paper. So this is a physics paper 1 written by Gauteng in 2024. It's a September exam. If you want to download the paper, check the description below. An air bubble in a tank of water is rising vertically at a constant velocity. The force acting on the bubble are x, y, and z as shown below. Okay, so they said that x is an upwards force. Y is a frictional force, as we can see, and then Z is the weight of the bubble. Which option is incorrect with respect to the three forces? Okay, so even before we look at these, guys, I don't want you to look at this and be like, could it be that? Just ignore that. Think about this carefully. We've got these three forces, right? We are told that the object is moving at a constant velocity. The only time that an object can move at a constant velocity is when all the forces are balanced, when the net force is zero, because we know that constant velocity means that acceleration is zero. So if we know F net equals to ma, and we know that acceleration is zero, then you end up with F net equaling zero. So if we had to then go put the F net over here, let's say upwards is positive, then you're going to have force x. Okay. You don't have to worry, should we say F or should we say X? Guys, it's multiple choice. You can write whatever you want here. You can literally be like, examiner's not really going to see it. Okay, so what were we saying? Okay, so you could say X is upwards. Then you could say minus Y minus Z. Because Z and Y are acting downwards, so I made them negative, and that's equal to 0. Okay, now if I had to take this, now remember they're saying which of these is incorrect. So if I had to take this and I move the Y and the Z to the other side, they would become positive. And so A can't be the answer because this is correct, but they said which of these is incorrect. So it can't be this one, okay? Now, if we had to get Z by itself, what would we get? If we come back here and we get Z by itself, if you take the Z over to that side, you end up with Z equals, and then you're going to have X minus Y. So, which is the same as if you just switch it around. It's the same thing. Okay, so Z equals to X minus Y. Do they have that? No, they have Z equals to X plus Y. So this one cannot work. So that means this one is incorrect, like they said. So that means this one is our answer, because they wanted to know which one is incorrect. If you had to carry on and you had to try look at this one, you would be able to make this. You would be able to make Y equals to X minus Z, which means that this one here, it means that this one here is correct, but we are looking for the ones that are incorrect. And then X bigger than Z, yes, you can see X is the biggest arrow, so it means that it's bigger than Z, and we can see that Z has a longer arrow than Y, so Z is bigger than Y. So this is correct. So these A, C, and D, they are correct, but they wanted to know which one is incorrect. I think you get the point. Ooh, elevator question. A person stands on a scale in a lift. Have you guys done that before? I actually have a bag that I carry around with me wherever I go, and I always have a scale in my bag so that if I'm in an elevator, I can, especially if there's chicks in the elevator, I can literally be like, how's it? How are you? Yeah, no, I'm good. Just going to do a bit of experimentation here, if you don't mind, if you just move to the side. And then I whip out my silver scale, put it on the floor, and they're literally giving me their WhatsApp number already, and I haven't even started my experiment. So yeah, go on Temu, order yourself a backpack, get yourself a scale. Remember that a lot of the scales don't come with batteries, so you might have to just pop down to Checkers, get yourself a pack of batteries, and you're good to go, guys. Yep, I don't charge for this stuff. I should. A person stands on a scale in a lift. The motion of the lift is given in terms of its acceleration. Okay, which situation represents weightlessness? So weightlessness is a feeling where you don't really feel. You feel like you don't feel the weight of your body, okay? So that would almost be the feeling when you jump out of a aeroplane if you were skydiving. Now think about this. We don't even have to go do all the fancy calculations here. I don't know if you've ever been in a lift before, but definitely when you're going upwards, does your body feel light or heavy? My body feels heavy when I'm going upwards, so it's definitely not that one. And check this out, guys. If you had to jump out of a parachute, I mean, not out of a parachute, if you had to jump out of an aeroplane, think about vertical projectile motion. If you just jump out of a aeroplane and there's no such thing as air resistance, or even just think of a ball that is falling, what is its acceleration? 9.8. So when something is falling at 9.8, that is called freefall. When its acceleration is at 9.8, that is just due to the gravity of the Earth. So there's not going to be any air resistance, nothing like that. The object is just falling. It's going to feel absolutely weightless. It's going to feel amazing if you're skydiving. It's just going to be like, bro, I don't even feel my body right now. So it's definitely just going to be this one where you downwards acceleration at 9.8. Now, for those of you that are curious as to why, for those of you that are just like, oh, wait, bro, that actually makes sense. Hoi, let's go. Then you can move on to the next question. That's the answer. But for those of you that are like, sir, how can we just say it's that one? Like, come on, prove it. How can we prove it? Okay, fine. I will prove it then, bro. So what we do is we look at the person. I want you to draw a free body diagram on that person. So what are the different forces that person is experiencing? Well, there's definitely the force of the scale pressing up onto that person's feet. Okay, so there is gravity going down. And that's it. Okay, so if we then had to go use F net equals to ma, and let's say downwards is positive because this thing is moving down, then we could say, okay, so it's going to be the force of gravity minus the force of the scale, and that's going to be equal to the person's mass. Let's say that this bra is 50 kilos. Okay, let's say that person's 50 kilos, whatever. So we say 50, and then the acceleration, we know that is 9.8. Right, now we can go a little bit further. We know how to calculate gravity. When I tell you that I want you to calculate the weight of an object, like if I gave you a 5 kg object, you know how to do that. It's always just mass times gravity. So you're going to take the mass, which is 50. Now, what is gravity? What is gravity on Earth? What is gravitational acceleration on Earth? It's 9.8. Now, I'm not saying that this is 9.8 because this is 9.8. Even if this said 3, I would have still put 9.8 here because this Fg is the force of gravity on Earth. That's got nothing to do with this number. It's just a coincidence that this number and this number are the same, okay? This number is the same as this number. That is because of that. If this was a 3, then I would have put a 3 there, okay? So make sure you're not thinking that I am putting 9.8 here because of 9.8 there. This 9.8 is because that is always the gravitational acceleration of any object on planet Earth, okay? Now, if we carry on, we don't know what the force of the scale is reading. And if we work this out, that should be... Actually, we're not going to work it. I was going to leave it alone. What you're going to notice is that these two are the same. And so if you had to go work out the value of F scale, what you are eventually going to find is that equals to 0. So what this scale is actually reading, if you had to look on the scale and what it's measuring, it says 0. So this poor guy's going to start having a bit of he's going to have a bit of a anxious episode. Suddenly he's going to start feeling his body like, wait, what is happening? Am I dissolving? Why is my mass, why is it saying that I weigh nothing? I weigh 0. Well, what's happening is that this scale is falling or accelerating down at the same gravitational value that all objects accelerate when they fall on planet Earth. So it's almost like this scale is falling away from his feet. His feet are trying to stay on the scale, but as his feet are trying to stay on the scale is also falling away at 9.8, and he's also falling at 9.8. So it's almost like him and the scale are going skydiving. There is absolutely no resistance. So think about that. The scale is falling away from his feet, and then as he's falling as well, so they're barely making any contact. It's almost like they're floating. It's crazy. Now, if you had to go retry all of this and you went and plugged in this value, then you would have put a 5 over here. Okay? But remember that this one here would have still stayed 9.8. Because that's got to do with the planet that you're on. And so what you would notice if you use this one is that this stuff wouldn't have cancelled out. And so the scale would have given a value. Okay, I hope that makes sense. You can go try this for any one of these. Some of you are like, but Kev, what about this one, 9.8? Bruh, this one's going up. That's going to be hoing this man, like compressing him. That poor man's going to feel super heavy because it's going upwards. Think about that. Imagine you've been in a lift before, and when that thing goes up, you can feel that pressure. But when it goes down, it feels less pressure. And that's the reason why. But in real life, lifts don't go like that. That would be crazy. We would all would be suffering. Lifts actually go down very slowly. Like nowhere close to this. This is free fall, dude. This is literally like jumping out of an aeroplane. I want you to imagine one more thing. Imagine you are in a lift one day and the cable snaps and that thing falls 200 meters down. Think about how that would feel. You would barely be able to stand on the floor. The floor would literally be falling away from you. And that's exactly what's happening. Okay, I'm waffling. I'm going on too long about this one. But the answer is C. A golf ball falls vertically downwards from rest in air and bounces back to the same height from which it was dropped. The graph below shows the acceleration of the golf ball with time. All effective friction can be or are ignored. Okay, let's just think about that. A golf ball falls vertically downwards. Okay, so let's just say here we've got ground. And then we've got a golf ball. And they say that it's initially at rest. Okay? And then someone drops it and it starts falling. They say that it falls and then it bounces back up to the same exact height. So it falls and then it bounces back up to the exact same height that it started at. Okay. So you understand? Hits the ground, bounces up, but it reaches the exact same height from which it was dropped. The graph below shows the acceleration. So before we even look at this nonsense over here, what would the acceleration of that ball be as it's busy falling? If we just think about vertical projectile motion, well, it would definitely have to be 9.8 meters per second, right? That is what acceleration is for any object on planet Earth that is free falling. So we know that for the first bit of time, this line must obviously be 9.8. That's what this value over here on the y-axis must represent, 9.8. We know that it stays 9.8 the whole time. Then suddenly the object is going to, crash into the ground. So there's a whole bunch of weird stuff that's going on over there. And then once it leaves the ground, it then carries on moving upwards, but the acceleration would still be 9.8 downwards. So this value would return back to 9.8, okay? And so this area here is where the weird part happens, where the ball is bouncing. Okay, so they said from all of that, they say a few statements. It experiences maximum speed at the minimum height. Okay, that does actually make sense. If you think about it, the ball is having a zero velocity over here at the top. Once it reaches the minimum height, which would obviously be the ground, just before, like when they say reaches the ground, they mean like literally as it reaches the ground. Wouldn't it be traveling the fastest in that moment? Yes, it would. So this statement is actually true, okay? Then this one says, its displacement falling is equal to its displacement rising. Well, that's actually going to trip up a lot of people. Because a lot of you, I know, you're going to say, yes, Kevin, this distance is the same as this distance. And you are 100% correct. But displacement and distance are not always the same thing. When they say displacement, there's direction involved. So let's say, for example, this is a 20-meter drop. Okay? And let's say they chose downwards as positive. Then the displacement over here is going to be, you're just going to say 20. But this displacement, when it goes from here to here, it's going to be negative 20. And so the displacements are not technically the same because of the sign change. All right, so this one won't be correct. And then this one says that it experiences a minimum speed at the maximum height. Correct, because when it reaches the top over here, we know that when it reaches its maximum height, what is its velocity or speed? You can call it speed in certain situations. Well, we know that that's 0. Is that not a minimum? Yes, so it's going to be... that's why they're not using the word velocity. Because that's actually quite clever. For those of you that are very technical with all of this, if we chose downwards as positive, then what would the velocity values be when you go upwards? Well, they would be like negative numbers, like -4, -3, -2. And so those numbers are smaller than 0. But that is why they didn't use the word velocity. They just used the word speed. Speed doesn't have a sign. So it is correct to say that the minimum speed that this object would ever get to is 0. It cannot have a negative speed. So there are no negatives in this question. It can only be positive number or 0. So the minimum is 0, and it will reach that speed at the maximum height. But if they put velocity here, well, then the question wouldn't really work out. Because then they could put that there to try confuse you. But remember, with velocity, it has a sign, and so you could get like -2, -3. And then you would say, oh, -4 is a smaller value than 0, for example, and then you would say that that is the minimum velocity. But because they specifically used the word speed, we don't have to worry about the negatives, and so the lowest number you can have is 0, and that would be up here at the top. And so this one is correct. So 1 and 3 are correct, and so the answer must be B. A ball of mass m moving at a velocity v collides head-on elastically with another body of the same mass moving with a velocity v in the opposite direction. Okay, so guys, what we pretty much have here is we have two objects. Okay, this one has a mass m and it's moving at a velocity v. This one also has a mass m and moving at a velocity v. Now, we would maybe imagine that when these two collide, they would stop. They would simply stop. However, think about it carefully. In a perfect world where everything is perfectly elastic, well, what would happen in an elastic world is that these two things would collide and they would simply just bounce off at each other with the exact same velocity. There wouldn't be any doubling or halving, nothing. Everything would just stay normal. So they would, if I had a wall over here and another wall over here, and everything was just elastic, those two balls would actually just keep bouncing into each other, going back to the wall, coming back, and it would go on forever because there would be no energy loss, and so nothing, it would just keep going on forever and ever and ever and ever and ever. So it says after the collision, both balls will have the velocity v. Both balls travel in opposite direction. You've got to be very careful here. Velocity and speed. We need to talk about that. So remember that velocity also has direction. So can we say that these two objects, these two balls, have the same velocity? No, we can't, because this one has, maybe this is 5 meters per second right, and this one is 5 meters per second left. So you cannot say that these velocities are the same. So after they collide with each other, you cannot say they have the same velocity, because this one is going to end up going that way, and this one is going to end up going that way. Although the number is the same, 5 and 5, for example, the one's going to be +5 and the one's going to be -5. So velocity, you got to be very careful. Whoever set these questions up, they're quite sneaky. Would the both balls travel in the opposite direction with the speed of v? That I agree with. I do agree that if this was 5 and this one was -5, the speed is 5 and the speed is 5, because speed doesn't have direction. So the 5s are just going to be 5s, and when you bounce apart, they're just going to be 5 and 5. You don't look at a negative when you're talking about speed. So I actually do agree with that one. Why don't I agree with C? Well, it says that both balls move at right angles. Well, hell no. What kind of world is that where these two objects are just going to bounce and then suddenly they're just going to move this way and this way? Nope. And then one ball comes to a rest and the other ball travels with a velocity of 2v. No, think about it. It's a perfect elastic collision. It's like an ideal world. They're literally just going to bump into each other and move apart. Maybe if one of them had a larger velocity than the other, or a larger mass, then something weird might happen. But if they are exactly the same and traveling at the exact same speed, well then, Bob's your auntie. A mass is lifted from rest on the ground to point H as shown below. Okay, so it was here, and then they're lifting it like that. See? Why don't you just lift it straight up, my bro? Why? Don't be doing this. Don't. P is the increase in the gravitational potential energy. Okay, so that's easy. We know that an object on the ground doesn't have any potential energy, because potential energy is mgh. Mass, gravity, height. We know that the height relative to the ground is 0. So we've got an EP there of 0. Then obviously if you lift it up, it's going to have a new potential energy, and it's based upon this height. It's got nothing to do with that height. That's what they're trying to confuse you. It's got to do with the vertical height. So it would now have a mgh, and let's say this is h1, so we could say that it's mgh1. Okay, now P is the increase, and then K is the kinetic energy at point H. So it was originally at rest, so kinetic energy is a half mv squared. So if it was originally at rest, then its velocity was 0 on the ground. Now it says that K is the kinetic energy at point H. Okay, so clearly it's got some speed or velocity now. So it is going to have some kinetic energy at H. Okay, which expression is equal to the mechanical work done on the mass to move it from the ground to point H? Well, it's literally this. We know that mechanical energy, right? Mechanical energy is just the kinetic plus the potential. So here, this thing on the ground had 0 potential, 0 kinetic. Now, all of a sudden, it's got potential energy and it's got kinetic energy. So how much energy was added to this object? Well, wouldn't it just be the addition of them? You just add them together? Yes. To what does the term red shift refer? Right, so I have explained this to you guys before within Doppler effect and how they use it to study galaxies and the way that stars can be shown to be moving away from planets. And so they say that the galaxy is expanding due to the whole like red shift, blue shift, all of that. So to what does the term refer? It's not the object's speed in space. It's not the color. It's got to do with the expansion. I hope you've seen my video on that where I talk about this whole how they use these machines to... okay, I'm going to explain it. For those of you that are not interested or you've seen the explanation before, you carry on. But for those of you that maybe have not seen it, let me take a bit of time and quickly explain it now. So I want us to imagine that the year is 2020. Hashtag COVID. And let's say that we've got planet Earth and we've got a star. Okay, so that's a star. You know, like the stars that you see in the night sky. All right. So, and then on planet Earth, we've got these little machines that can measure frequency. Let's say that it looks... Okay, now why am I drawing like a person? Okay, let's do it like that. Okay, so here we've got this machine and it's busy measuring the frequency from the star, and let's say it measures 100 hertz. Okay, then we fast forward to the year 2000. Okay, let's make sure Kevin, my science, is still relevant in the future. Let's go to the year 2040. So all the kids watching this in 2040, am I still alive? That would be awesome if I am. Okay, so actually, why am I saying that? You know, let's put positive energy. I will be alive. And okay, so what happens now is we've got, okay, so they've got that same star. These guys have been tracking this star the hele date. And let's say that this star is now registering, or it's giving off a frequency now of, let's say it's now 70 hertz. Okay, it has to be less than this number. And that's because of reasons I'm going to explain now. So I want you to think about this. Frequency, remember, that tells you how many cycles are arriving per second. So with this one, there were 100 cycles arriving per second. Here it's only 70. So I want you to think about like the Doppler effect and like thinking about like an ambulance driving towards you. When the frequency is becoming lower, so it went from 100 to 70, is that normally when the objects are moving towards you or away from you? Well, we know that if you have like a person over here, okay, and then there's an ambulance coming towards them, and it's giving off a, okay, that's meant to be a siren, and it's giving off this frequency. If the ambulance is going towards the person, then what happens is that these waves get really squashed up, and what we see is that there are more waves or more waves per second, and so we say that the frequency goes up. Think about the word frequency. Frequent. If someone goes to the shops frequently, it means that they go to the shops often. So when you have a high frequency, it means that you see a lot of them, and that can only happen when the object is moving towards this person, because then the waves almost end up being squashed up. But as soon as the ambulance is moving away from the person, then what happens is that the frequency actually drops and the waves become more spread out. Okay, so what scientists have observed by studying and following stars over the years is that as the years are increasing, they're noticing that the frequency is becoming less and less and less. So would that mean the ambulance is coming towards the person or away from the person? What causes the frequency to become less? Well, it's when the ambulance would be going away. And so what scientists are discovering is that the stars are moving away from planet Earth, which implies that the universe is expanding. It's not coming closer and closer together, it's expanding. And that is why our answer is C. Which of the following graphs has a slope that is equal to Coulomb's constant? Now, at a first read, you might be like, yay bro, wat gaan nou aan? Yay. There's not even any numbers. Okay, guys, but relax. Check here. We know Coulomb's constant. Where do we see that? We see that in this equation, right? Electrostatics. So what you're going to go do is you're just going to go and, oh, but I see they're using E over here. Okay, so that's not the only place that we see it. We also see it here. K, Q over R squared. Okay, so yeah, it's not going to be this one because they're using E. So I want to use the one with E. Okay, now, if K is the slope, then you always have to think back to straight line, y equals to mx plus c. Now in this scenario you can see we don't have a plus c part, and that is because our y-intercept, we can see we're going through the origin in all of our graphs, so we don't need to worry about that part. So that means that the gradient is always the part that is in front of whatever you see at the x. So if this is the gradient, then what is the x value? Well, the x must be the q over r squared. So now which of these have a q over r squared? Boom, here it is there, and then the y value is E, like we can see over there. Okay, so then the answer must be C. Let's not circle all of those. 3 resistors are connected in a circuit as shown below. Okay, so we've got these 3 resistors. Now it says that a 4th resistor is connected in parallel to the 4 ohm resistor. So they're going to connect another resistor over here. Now, compared to the original, how will the power in the 8 ohm and the 4 ohm resistors change? So they want to know, how does the power change in the 8 ohm and how does the power change in the 4 ohm? Right, so we need our power formulas. We know that there are, well, there's this one, then there is this one over here, and then there's also I squared times R. So if we now add another resistor to the circuit, because we're adding the resistor in parallel, remember that the more resistors you add in parallel, you actually make the overall resistance lower. Some learners really don't understand this. I want you to imagine that you are walking and you're walking into a shopping center and there's only one door. Now let's imagine there's 50 people behind you and you all have to go through one door. Pretty difficult, right? If we then open up 3 other doors, then suddenly those 50 people, there's multiple pathways, and so it allows the 50 people to get through much easier. So notice that when you add resistors in parallel, even though you're adding more doors that have to be opened, it still allows things to flow easier. It's only when you add resistors in series that you begin to increase the overall resistance, and it makes it more difficult for people to flow. Imagine 50 people having to open this door, then they close it, and then they open this door, and then they close it, and then they open. It's like walking into a bank having to wait for that stupid green light. The other day I tried to rob a bank, I get caught there, and the thing doesn't want to turn green. Suddenly I've got like the police. Like, come on, man. Make life easy for me, yeah. Okay, no, but you get what I mean, right? If you're going through doors that are immediately after each other like this, it's very difficult for these people to walk through all of those doors. But as soon as you make it in parallel, you actually allow overall resistance to become less. Resistance is like something that tries to slow things down. But when you add more resistors in parallel, you actually make the entire process better. And so the overall resistance goes down. So the current actually goes up because people can now flow more easily. And current is the flow of electrons. But in a situation like this, when you add more resistors, the overall resistance goes up. And then the overall current or the flow actually goes down. So they added another resistor in parallel. So this area here has now going to have a lower resistance. And so the overall resistance in the whole circuit is actually going to go down, and so the overall current in the whole circuit is going to go up. So if you can imagine, the amount of current that's now going to flow through here is going to be way better or way faster than it was when we didn't have that. People were struggling to get through this whole circuit, okay? I know it's a bit weird thinking about, but Kevin, this part here doesn't change. I know, but obviously I'm using people to explain, but it's not actually people walking through here. The way it works with electrons is a bit more complex. So if you can change the current, the resistance in just this area, it affects the current in the whole circuit. Okay, so the overall current of the whole circuit is going to go up. So even this 8 ohm is going to feel an increase in its current. Okay, so if we then not use this formula or this one, but we just look at this one over here for this 8 ohm, the R is still going to be 8. It is still 8 ohms. This part doesn't change. Yes, we're changing the resistance here, but that is still an 8 ohm, and the current we said has gone up. So what would happen to the P value for this one? Oh, it would go up. So we definitely don't want to choose A or B. We want the power of the 8 ohm to go up. Now, when you look at the 4 ohm, you might say, oh, yeah, Kev, it's also going to go up. Hey, brother, because you just said the current's going to go up. Yeah, but think about this. You've now got another door. So yes, the overall flow through this section is going to be faster, but now remember that originally all of the current was going to go through this one door. Now suddenly we've opened up another door. So now yes, there's more current that's able to travel, but some of it's going to go through the 4 ohm and some of it's going to go through the other or the brand new resistor. So what would probably happen is that this overall current is going to go down. Even though the current in the main circuit has improved or it's gotten faster, some of it's going to go through here, but a lot of it's also going to go through this new door that they've now opened. So this 4 ohm is probably going to notice a lower current than it noticed before we added the new door. Does that make sense? So what we would notice is that this one's power is actually going to go down, and so the answer would be D. An immersion heater can be operated either using AC power or a DC source. The graph below represents the potential difference when you use an AC power supply. What DC voltage would produce the same rate of heating? Okay, guys, actually very interesting. So let's actually make this quite easy for ourselves to understand. I want you to take I'm going to use a weird example, but let's say you take a kettle. Okay, so we have a kettle where we use to boil hot water. Let's try draw a nice picture of a kettle. Then it's got a handle, and this is a kettle. Now let's say we buy this kettle from Macro, and let's say this is a very special kettle because this kettle, you can either use the plug that it came with, and you can plug it into one of your plugs at home. If you plug it into one of your plugs at home, into the wall socket, then it's going to be getting power from Eskom, and that uses AC. That's when it goes like this. That is how Eskom supplies electricity, like that. Okay, so that would be normal. That is how we actually use most of the things at our houses. If you go look at your fridge right now, television, your kettle, all the main devices, they plugged into the wall, and so they are receiving power like this. We call it AC, alternating. But let's say there was a really special kind of kettle that instead could use batteries. So you could literally go to the shops and literally go buy batteries. You wouldn't even need to plug it in. So you just go buy some Energizer batteries and you plug it in. That's not possible because these batteries, it wouldn't work out. But I'm using an example. So this is just a battery. Now, when it's a battery's voltage doesn't go like this. A battery's voltage just stays constant. We call it direct. So let's say the battery has a voltage of 5, for example. Okay, actually, no, that's what this question's all about. So, okay. So here, if we look at this part over here, we know that that's this part where you're using your AC power. And we can see that sometimes the voltage goes to 12, and then it goes back down to 0, and then it goes to minus 12. The minus 12 is just because it's going in the opposite direction, but it's still just 12. The kettle is like, away, 12 volts. So if I had to ask you, what is the average? If some of it goes to 12, some of it goes to minus 12, what is the average? Well, some of you might say 0. Technically, that is correct, because if you take the number 12 and the number minus 12 and you work out the average, you actually do get 0. But obviously, the kettle is still working, so it can't be 0. So what else would you maybe say? Well, Kev, you did say that the kettle doesn't really know about the direction. So if it sometimes sits at 12 and then sometimes sits at 0, wouldn't the halfway maybe be 6? Scientists used to think about that in the past, but you know, it's not exact on a sin or a cos graph. It doesn't exactly just stay half of the time. It's not at 12 half the time and 0 half the time. It's a bit weird. So what we rather do, instead of just saying 12 divided by 2, we actually say 12 divided by square root 2. We use a square root 2 instead. So let me explain though. If your kettle at home is plugged into the power like this, and this is what the power looks like, but instead you rather want to use a battery, the question is, what strength or voltage should you go buy at the shops? Should you buy a 12 volt battery? No, it doesn't need to be 12 volts all the time, okay? Because remember, whatever battery you buy, it's going to stay like that constantly. Okay, should we go buy a 6 volt battery? No, because we just said that it doesn't actually work out exactly like that. So then, what should we do? Well, it's going to be 12 divided by square root 2. We use square root 2 instead of 2. And, oh, they haven't even simplified. And so C would be the answer. So what that means is that if you don't want to have your power, if you don't want to have your kettle plugged into your power at home, rather want to use a battery, maybe you're going on a camping trip. By the way, we don't power kettles with batteries. As I told you, it's just an example. Then you can go buy a battery that has this voltage over here. If I work that out for you, by the way, it gives us a value of 8.49. So if you could go buy an 8.49 volt battery and you could constantly supply 8.49 volts to this kettle, it'll actually work just fine. It doesn't have to go all the way up to 12 and then all the way down to 0. It'll work if you just plug in an 8.49 volt battery, because it'll just stay there. Does that make sense? So that is what this question is asking. What DC voltage should we go by so that it almost gives us the same effect, so that the kettle doesn't really notice any difference? The work function of a metal is W0 equals to that. Yes, we know about that. We know that this whole chapter of the photoelectric effect, where we've got light shining onto a metal, we know that the governing equation is typically that. The energy of the light is equal to the work function plus the kinetic energy. But we also know that there's this other formula that goes like this. And we can use this formula for this part and this part. When we use it on this part, it just becomes that. And then when we do it on this part, then it just becomes, we just change it to F0. Okay, so that's all that they're really telling us over here. We know that. Now they say that if the metal is illuminated with light with a frequency of 3F0, what would the maximum kinetic energy of the photoelectrons be? Okay, well, this is interesting. Normally, when we calculate the energy of the light, which is this one, we normally use the frequency. That of the light, but they've given us that. They've given it to us in terms of the threshold frequency, so we can actually plug that over here. Because remember, this part is the light, and then this part here is the metal itself. Okay, so they've given us the light. They said that is illuminated with light of frequency that. Okay, so if we've got this formula, then we know that we can replace this formula with HF, and this one can be replaced with HF0. But now in this particular question, they've given us this frequency in terms of this one. So they almost went like this. So we can now replace this with 3FO, and so you end up with 3HFO equals to HFO. The O is just a subscript, okay? It's actually like this, okay? And plus EK. And then if you had to take this HFO to the left, you end up with 2 HFOs. So what would the maximum kinetic energy be? 2 HFOs. So here are all the questions we're going to do, 2.1 up to 2.4, but I will be splitting them up onto individual pages. So let's see. A toy train of mass 2 kilograms. Okay, so here we have a train that is 2 kilograms, and a toy car which has a mass of 1 kilogram are attached by a light string. The car system is pulled up a rough slope at a constant velocity. Nice. With a force T2 acting on the rope. Okay, this diagram was a little bit blurry. Okay, so it's, I don't know why the 10 degrees is, yeah, it just looks a bit weird, right? So it should be, the 10 degrees is that angle over there, okay? Now, okay, so the first question is, explain the term net force or resultant force. So before we go get the technical definition, let's just talk about what net force is, okay? So if we have a box, and let's say there is a force of 7 newtons that way, and there's a force of 2 newtons that way, then what is the net force? Well, the net force is going to be 5 to the right. Can you see? Because if you have 7 going to the right and 2 going to the left, then the overall effect is the 5 newtons. And that is what we mean when we say net or resultant. It's the overall, it's like the summary, or it's the result of everything put together. So there it is there. The net force acting on a body is the vector sum. I don't really use that one too often. The one that I've seen more often is this one over here. It is a single vector that has the same effect as 2 or more vectors added to, or 2 or more vectors together. Let me show you what they mean by that. Remember I showed you earlier, I said 7 newtons and then 2 newtons. What did we say the overall effect was? We said that that is 5 newtons to the right. So this is called the resultant. And what we are saying is that the resultant is a single vector, see how I only have 1, having the same effect as 2 or more vectors together. So these two combined is actually just going to do this. And I could have added more. We could have added like 7 forces on here, or 100 forces. It doesn't matter. If you add it all up, you would eventually end up with 1 resultant vector. Next question says, draw a labeled free body diagram for the toy train. Okay, so in 2024/2025, the department made a few changes, and what you'll notice is that obviously some of my older videos, which I'll probably have to go back and change at some point, but they don't want us to, you know how with on a slope you get FG parallel and you get FG perpendicular? They don't want us to show that anymore, okay? Yes, we can use those in calculations obviously, but on the free body diagram they don't want to see those components anymore. They just want to see gravity, which always acts vertically downwards. You could say FG, you could say W, there's a whole bunch of different things. Now, what other forces are there? Well, notice that this is a 5-mark question, so there's going to be 5 forces. So we can see that we've got T2, and then, okay, so we can put T2. So T2 goes like this. You don't have to show the angle, T2. And then normal force always goes at 90 degrees to the surface. That you still show normally like that. You can say N, you can say Fn. They have a couple options that they allow. Then there's going to be this force of the rope, which is going to go, it's not exactly in line with this one, because remember this one is inclined at 10 degrees. So that one's going that way, but this one's going that way. So it's going to be more like that, okay? And that's going to be T1. And then friction. Do they talk about friction? Well, they say that it's a rough slope. So there's definitely going to be friction also going in that direction. So you could just say friction like that. So notice how we have 1, 2, 3, 4, 5 forces. So back in the day, before like 2024, we could, if we wanted to, break FG up into parallel and perpendicular. Some of my videos you would have seen still have it that way, but obviously when the department makes a change, I can't just suddenly overnight change all my videos, and I'm not going to take them all down. So yeah, just look out for that, okay? We're not allowed to show components anymore. And so just to show you that these are some of the allowed, this is straight from the memo. You can use W, you can use FG, you can use FW, you can even say weight, gravitational force. They're pretty lenient. You can say normal force, you could say FN, you could say normal force like that. You could even write it out. You see, so there are different options, okay? Sure, they even allow, okay, yeah, T2 is, I guess, an applied force. So yeah, don't feel like, maybe your teacher, I don't like it when teachers do this, but maybe your teacher was like, I'm going to give you 0 for the whole question if you use N instead of FN, for example. Some teachers are really weird like that. And then it's like, bruh, just relax. When we get to the finals, you know, we're allowed to use these different formats. Here they say that the tension force, T2, is now increased to 20. So what was it before? Did they tell us? Tell us in the previous one, guys. Constant by the rope with a force T2. Okay, they don't say anything, but they do say here that it is increased. Okay, so we can assume that it was originally less than 20, causing the system to accelerate. That makes sense. Can we talk about that quickly? So we know that they told us that this system over here was originally moving at a constant velocity. That is what was happening originally. So if you had to stand on the side and watch the system going past you, it was moving at a constant velocity. And remember that when something moves at a constant velocity, we said earlier that the net force is 0. So it means that this system is perfectly balanced. Now suddenly, if you then take this force and you increase it, well then obviously the system won't be balanced anymore, and so the system will begin to accelerate. What does that mean? Well, if it's constant velocity, let's say for example it was moving at a constant velocity of 5. I'm not saying it was, just an example. So let's say it was moving at 5 meters per second. When it's moving at a constant, it means that it will not change. So the 5 will remain 5. So it will just keep going up the slope 5 the whole way. If you had to watch it, if you were standing on the side of the road and you watched this coming past you, it would just keep moving at the same speed, if you want to think of it like that. It wouldn't be going faster or slower. It would stay the same speed. Then suddenly you begin to add a force over here. Well, then the speed, the object's going to begin to accelerate. So you're going to notice that this 5 is going to start changing. It's going to go 6, 7, 8, 9. It's just going to keep increasing because it's accelerating, okay? So they're saying that causing the system to accelerate. Calculate the magnitude of this acceleration if the friction force on the car is that and that on that is that. Right. So we typically, what we've done before, guys, whenever we have these system questions where we've got two objects, what have I always told you to do? Step 1, draw a free body diagram on both objects. Step 2, F net equals ma for both, and then solve simultaneously. We then do F net equals to ma on both, and then we just solve simultaneously. And the unknowns that we typically are going to solve is acceleration and tension forces or applied forces. Okay. Sometimes they would have given us the tension force already, or they gave us that one, but sometimes they'll give you this one as well, and then the question says find the acceleration. Then you don't have to do simultaneous, but then you'll see the mark allocation probably be like 3. But yeah, even if you did try to use this when you don't have to, it still works out. This always works, okay? So we already have a free body diagram on the train, but let's just go draw it again for ourselves. So we said that there was T2, we said there was normal force, we said there was, okay, that's actually more like there, and then we had there, and then normal force would always be at 90 degrees to that, and then gravity. Okay, so we had T1, and we had friction. Okay, and then, so it says draw a free body diagram on both objects. So now we're going to go do the car. So the car I'll do in green. So for the car, let's have a look. It's definitely got T1 going parallel to the slope. It's going to have gravity, of course. All objects have gravity. It's got normal force. And then it's going to have friction. It's got its own friction because it is a rough slope. So we can say F. Now, we've got to be careful. This is not the same f as each other, so maybe we should just be careful there. Well, actually, it's fine. I mean, you must just remember for yourself, they don't really give you marks for these free body diagrams. They only gave you the marks for the free body diagram in that first question. So we can just maybe make a note for ourselves. Remember that this is for the train, this is for the car, and this is obviously the car, and this is obviously the train. Okay, so we've done a free body diagram on both. Now we're going to go use F net equals to MA on both. So if we go do it for the train, okay, I'm going to say that up the slope is positive, and now it's really easy, guys. We can see that we're going to have to use this force. We're going to have to break this one up into its components, and we're going to use these two. You're not going to use normal force because that is perfectly at 90 degrees to the slope, so we don't use that. But we're going to use all the other forces. Okay, so, and remember that the orientation is the slope itself, okay? So I don't want to use T2 like that. Instead, I want to remember that there's a triangle here. I know that there's a T2 in the Y and a T2 in the X. I want to use the X version, so I'm going to say T2 in the X. Yes, you could use cos and 10 and all of that and change it right now, but I'm just going to leave it as T2 in the X direction for now, okay? And then we're going to say minus T1 minus the friction. I didn't have to make T1 in the X or T1Y because T1 is only in the direction of the slope. You see, T1 is perfectly aligned with the slope. So we don't have to break it up into components. And then minus the friction, which we said, but let's just make sure we remember that that's the friction due to the train. And then, this is the part that I don't like, the fact that the department doesn't allow us to show the components on the diagram, because some learners might forget that there is components here. So remember that FG, actually, now remember, you're not gonna, when you can put the FG perpendicular, you can draw your own little free body diagram on the side if you want. Just don't put the components when they ask you to do it officially over there. But you can actually just remind yourself here that there's a T2, there is a, actually let's put that last, there's a T1, there's a friction force, and then remember that this FG can actually be broken up into FG perpendicular and FG parallel, right? Sorry, it's a bit squashed up here. Maybe that's why they don't want us to use components. And then there's a T2. Okay, so we're not going to use FG perpendicular because that's completely at 90 degrees to the direction that we're moving. So that's why we don't use normal force and we don't use that one. But now we're going to have FG parallel, so that's going to be minus FG parallel, and then all of that is equal to MA. Okay, but now let's go fill in as much as we can. So T2 in the X direction, well, we know the value of T2, it's 20. So if I had to draw a triangle now, we've got 20 over here, we've got 10 degrees, and we want to find what is T2 in the X direction. So you could go use grade 10 trigonometry, SOHCAHTOA, and what you're going to notice is that we're going to have to use cos. So you're going to end up eventually getting 20 cos 10 over there, okay? And then you're going to say minus T1, which we don't know, it's one of the unknowns. The friction of the train, so they say here, the force friction on the car and then that on the train is 2 newtons. Now FG parallel, remember, is mg sin theta. So it's the mass of the train, which was 2 kilograms. G is 9.8. And then sin, now you got to be careful. It's not the sin of 10. It's the sin of the slope when you are using this. It's the sin of the slope. So that's 20 degrees. Okay. And that's then equal to mass, which is 2, and A, which is unknown. So you see how we have 2 unknowns? Hence, we're going to have to solve simultaneously eventually. Now we can go simplify a little bit further, but don't round off your values. Like maybe keep like 4 decimals for now. Okay, we're not going to the final answer yet. So if you type this in your calculator, keep it as like 19,6961. I just wrote the first 4 decimals. And then this we can, actually, sorry, what we could have done is just put this, and this all on your calculator. Okay, so 20 cos 10 minus 2 times 9.8 times the sin of 20. Okay, but don't round off. So that's going to be 10,9925. I'm not rounding off the 4th decimal. I'm just writing the 4 decimals as exactly as I said on my calculator. And then there's going to be a minus T1 equals to 2a. And then I'm going to get T1 by itself. So T1, if I bring T1 to the right, it would eventually be 10,99 minus 2a. Okay, so that is T1. Now we can go do the F net equals to MA, but now on the car. So F net equals to MA for the car now. Up the slope positive again. So now we just look at its free body diagram. So remember, we ignore all forces that are at 90 degrees to the surface. So if you look at that being the surface, then we know that normal force is always at 90 degrees. So we ignore normal force. We're not going to use that in the F net equals to MA. Now this one is not at 90 degrees. Remember that FG can actually be broken up into, so we've got normal force, we've got its friction. Now remember that FG can actually be broken up into FG perpendicular and FG parallel. So if you now look, if this is your surface, then we can see that the normal force is at 90 degrees, so we ignore it, and then FG perpendicular is also at 90 degrees, so we ignore it. But everything else gets included. So we're going to say T1 minus the friction minus FG parallel, and then we're going to make that equal to MA. All right, and now let's go fill things in. So T1 is an unknown, obviously. F is the friction on the car, which is 1.5. Now remember, parallel is always mass, gravity, sin, theta. So mass is, what is the mass of this car? It's a 1 kilogram car. So it's M, gravity is 9.8. And then sin of the slope, there we go. And then mass is 1, and then acceleration. So notice 2 unknowns. All right, so now what I'm going to do is I'm just going to type this in my calculator, but some learners make a little mistake here. They start by typing in 1.5. But guys, it's negative 1.5, so you must put that on the calculator. Negative 1.5 minus 9.8 times sin 20. And so I wouldn't round off yet, so keep it as 4.8517 equals to 1a is just a, right? Okay, but now I want to get T1 alone. Or no, we don't have to really, because you see over here, we have T1 as this, so I can now plug that in over here. So I can now end up getting 10,9925 minus 2a. So you see what I've done? I've just replaced that inside here, and then minus 4,8517 equals a. Now we just solve for a. So we take this to the right, we put those two numbers together, and so 10.9925 minus 4.8517, and that's going to give 6.1408. See how I'm not rounding off just yet? And then on the right, you're going to end up with 3a. When that goes over, it's going to join this one. And then you divide by 3, and we should get a as 2.05 if we now round off. 2.05 meters per second squared. Okay, what did they want? Calculate the magnitude of the acceleration. Oh, magnitude. So we don't have to give direction. Perfect. And that's it. They didn't ask us to calculate T1, but you could if you wanted to. But yeah, maybe that's going to come up in the next question. And here's the last one. So it says halfway up the slope, the string T1 breaks and the car rolls down the slope. Okay. Does the friction force on the train increase, decrease, or remain the same while still moving up the slope? Explain the answer. Well, we know that friction, if you break it up into its components, it's the coefficient, or specifically kinetic friction. Why kinetic? Because we are still moving. and then that's multiplied by normal force. So if we can see what happens to these two, then we can answer the question. So this part here is coefficient friction, and it depends on the surfaces. Okay, so if this rope snaps, does the surface change to a different material? No. Are the wheels of the train going to change? No. So we can say that this part does not change. Now, to analyze whether the normal force is going to change, I want us to go do a very, on the next page, I'm going to do a very large free body diagram showing all the components on this train. So, for the train itself, we know that it's got this T2. We know that it's got friction. It's not going to have T1 anymore because there is, but let's just put it there for now because we know that the rope snaps, right? But let's just say that it's there for now. Okay, I want to actually make this a bit bigger, the space. Okay, T2. Now, friction. And then for now, let's just put T1 in there, but we will take it away just now. Then we've got normal force, which is always at 90 degrees to the slope, which is in this direction. So that's going to go like that over there. And then we've got gravity that goes straight down. Okay. Now, to be able to analyze this nicely, I want us to break this up into its components. And so that is actually going to be FG perpendicular. And let's take T1 away now, FG parallel. Then I also want us to remember that this one has components as well. So, because remember, your slope is this one. Remember, the slope is running in that direction. Sorry, like that, at 20 degrees. So this is your slope. Okay, so this is not on the slope, which means it has components. It's going to have a y component. Oh, and I'm also going to take this away. Okay, so T2 is going to have a y component, and it's also going to have an x component. Okay, and then I'm going to take this away. So that is what it looks like in component form. Now remember, you're not allowed to show this if they ask you for an official free body diagram, but you can do this as a little diagram on the side of the page for yourself. It's quite stupid, right? Anyways, the reason we did that is to have a look at what factors are going to affect the normal force. Because the normal force is in this orientation over here. Now we know that we can use F net equals to MA, and you can use F net equals to MA in this orientation, which we already did earlier, but you can also do it in this orientation. Okay, but remember that in this orientation here, the object is not accelerating. I don't know about you, but if you had to watch this train, it's not going off the surface or into the ground. It's moving along this direction. So the acceleration in this direction is 0. Okay, well, we could say acceleration is 0, and so F net in that direction is 0. And we could choose that direction as positive if you want. So what forces help with normal force? Well, you've got normal force plus this one, they're acting in the same direction, okay, and then minus this one, and then that must all be equal to 0. Right, now if you had to go work out the normal force is going to be equal to FG perpendicular minus T2 in the y direction. So if we look at the normal force and its components, well, you can see it's got to do with these two. So FG perpendicular is always going to be mg cos theta of the slope minus T2y. So if this rope breaks, do any of these change? Well, the mass of the train doesn't change, gravity doesn't change, the angle of the slope didn't change, and the value of T2 is still going to be 20. So working this part out, and this little slope, this little angle here is not going to change. So nothing is going to change with the normal force. So if we now go back to their question, they said does the friction force on the train increase, decrease, remain the same? Well, we proved that this stays the same. We've just proved that that stays the same. So it would remain exactly the same. And then we'd have to explain. So we would say remains the same. Now the reason is that is equal to that. And we could say and both this and this do not change. Done. A tennis ball falls freely from rest from point A, which is 44 meters above the ground. The time taken to fall to different positions B, C, and D. Okay, so it's given in terms of T. Okay, so to go from A to B, it only took 2T. To go from B to C took a time of T, and then to go from C to D took a time of 3T. So that doesn't mean 3 seconds. It doesn't mean 1 second, and that doesn't mean 2 seconds. They're doing it in time in terms of T. Okay. So the first question is define the term free fall. So what is free fall? Free fall is when an object is falling due to the influence, or it is moving due to the influence of gravity only. That doesn't mean it's going downwards. Did you know that if you have ground and you have a tennis ball and you drop that tennis ball, the only force acting on it is gravity? Yes, in real life we also have air resistance, but we ignore that in grade 12. So there's no air resistance, and unless they give you a question that has air resistance, but I've only ever seen that like once, and it wasn't difficult at all. They literally said it has air resistance, and the air resistance is 10 newtons. It's just like a friction force. Anyways, but if the object falls, it's just under the influence of gravity. Then when it hits the ground, and then it starts going upwards again, why would the ball, when it's going upwards, why would it be slowing down? Because the only force acting on it is gravity, and gravity is always acting downwards, so it's going to try slow the ball down. So it's not only when objects are falling, it could even be when objects are going upwards. So it's actually got nothing to do with fall. It's got to do with when the only force acting on the object is gravity. So how would we answer this? You would say that free fall is motion of an object which is due to gravitational force only. Or you could have said which is only due to gravitational force. Okay, this one over here, calculate the value of T for 4 marks. Okay, let's rather do it here so we have a bit of space. Okay, so right. Let's try to figure this out. So a tennis ball falls freely, which is 44 meters above the ground. The time taken to fall to the different positions. Okay, so we don't know anything about this distance to here to here. We only know the total displacement over there. So let's go work out the time to do that, and that'll help us. You'll see now. So we know that there's different formulas we can use. And so let's think about what we have. We know that it falls from rest. So we know that at the top here, at velocity of A, we know that that'll be 0. We don't know what the velocity at D is. Some learners, they say, oh, okay, if it's going to be 0. No, they mean as the moment that it hits the ground. So that's not 0. We do know the delta Y is going to be 44, but be careful. It could be negative 44 or positive 44, depending on what you choose as positive. But the point is we do have that. We also have acceleration. So we don't have... Oh, and we're trying to find time. So we definitely don't want to use this formula, or sorry, this one here, because this one doesn't give us time at all. So we could probably use... Okay, we're not going to use this one either because we don't have the final velocity. So that means we wouldn't use this one because we also don't have the final velocity, and so that means we're going to use this one over here. So we could say delta Y equals to V initial delta T plus a half A delta T squared. Now you can choose whatever you want as positive. I'm going to just choose downwards. Okay, so then if you choose down as positive, then the displacement is 44. The initial velocity is 0. The time, now the time is going to be, well, there's different ways you could do this, okay? Okay, let's just, I'm trying to think how you guys would want to do this. Okay, here's the two options. You could either go plug in 2t plus t plus 3t, which is 6t. You could either plug 6t into here, okay? Or you could just go leave it as delta t. But remember that this t and this t, they're not the same thing. So that might confuse some of you, okay? They shouldn't have used the t over here. These little things that just, yeah, I don't know, can cause issues. So I'm going to go plug in the t as all of these added together. I think that'll be the least confusing, okay? Now, acceleration is 9.8, and it's positive because we are going down. And then here I'm going to put 6t squared. Okay, so then you're going to end up with 44 equals to 0 plus 176.4 t squared. Okay, and so then you just end up with 176.4 t squared equals 44. Now some learners are going to say this divided by that, but remember it's this one divided by the 176.4. So you're going to end up doing this. Okay. And then you can go solve this thing. Lovely. You know you're onto something when you get a nice answer like this. T was 0.5 seconds. Okay. So it was 0.499 and then it just rounded off. So let me say 0.50 and that's seconds. So now that is the value of t because this t was this t. But if you had just gone and left this variable as that, like in the formula, or that, then this t, you would have got, that t wouldn't have been the same, so you would have ended up getting a slightly different answer, but then you would have said something like that t that you worked out is actually the same as 6t, and then you would end up dividing by 6. So you probably would have gotten an answer of 3, I would imagine, if you just kept it like that. Over here as well, you would have gotten an answer of 3. And then you would have said that 3 is the same as 6t, and then t would have ended up being a half. Okay, so we now know that this value of t is 0.5 seconds, okay? These little t's, each of them represents 0.5. So that means that this area here is actually 1 second. This area here is actually 0.5 seconds. And then this area here is actually 1.5 seconds. So it says this question, calculate the height of the ball at point C. When they say the height of the ball, they mean height of the ball relative to the ground. So what we could go and do is we could go work out this distance over here. We can do that so long. So we could actually use the same formula that we used because we still don't have any final velocities. And we could say we don't know what the distance is from there to there, but we know the initial velocity was 0. We know that the time from A to C is going to be 1 plus 0.5, which is going to be 1.5 seconds. Acceleration is going to be positive 9.8 because downwards is positive, and then 1.5 squared. Okay, so if you had to work this out, this won't be the final answer, by the way. Gives us, I'm not going to round off, 11.025 meters. What that is, what you've just worked out there, is the total distance up to that point over there. Some of you, I know how some of you think. You're going to say, Kevin, isn't this distance just going to be 22 meters? Because this time, if you add it together, it's exactly the same as that time. But guys, you got to think about this very carefully. The object is not falling at the same speed. It's getting faster and faster and faster. So in this 1.5 seconds, it's going to cover less distance than in this 1.5 seconds. Because in this 1.5 seconds, it's moving faster. So think about that. It's moving for 1.5 seconds at a slower velocity here, and then 1.5 seconds at a faster velocity. So this distance is going to be more. They've drawn the diagram in a way that is not drawn to scale at all, but you got to be careful. I've seen a lot of learners do that. they think that if the time is the same, then the distance must be the same. But it can't be because the velocities are not the same. All right. So what we've just worked out is from here to here is 11.025 meters. We know that the total distance is 44. So then what would this distance be over here? Well, you could just say 44 minus 11.025, and that'll give 32.98 meters. Everyone's favorite graphs. Okay, obviously that was a joke. I know you guys don't like these things, but let's have a look. So let's just fill in what we have so far. We still remember that the time is 0.5 seconds, and this was 1.5. And then we've just worked out now that this distance here is 32.98 meters. Okay, let's see what they want. So if after the first bounce, okay, so the ball reaches point C. Okay, did they talk about bouncing earlier? A tennis ball falls from rest. The time taken to fall to different positions is given as that. Okay, so originally the question was just going down, but now they're talking about a bounce. Okay, so the ball's gonna hit the ground. They said that if after the first bounce the ball reaches point C, okay, the ball reaches point C, okay, sketch the position time graph for the ball from the moment it is dropped until it reaches point C after the bounce. Show the following on the graph: the time values at point D and C before the bounce. Okay, we've got those. It's going to be this time over here and the time to get to here. And then, in terms of T. Okay, so they still want it in terms of T. And then they want the heights at A and C. That's easy. And then take the ground as the point of zero reference. Very nice. So that means your graph doesn't have to look like this. We're not going under the graph because your ball can't go under the ground. So we can actually make a graph that looks like that. Now they want a position time graph, so we could literally say here position in meters and then time in seconds. Right, now it's always very easy. Think about this. If this is the ground, then at the very beginning, how high is the ball? Well, the ball is 44 meters up, so we're going to start there at 44 meters. Okay, and then the ball literally is just going to fall. Boom. Okay, so it falls. We assume that it hits the ground and then immediately jumps up. There's no delay. Okay, and then once it hits the ground, we know that it bounces up again to point C, which is like, we said that this was 32.98 meters up. So something like, they're not really going to mark you according to the scale, I can promise you that, but let's say up to there, for example. Okay, now let's make sure we add all the values. So they say add the time value at point D, but in terms of T. Okay, so at point D, that's when we reach the ground, so that's 2T plus 3T, that's 6T, so we put 6T, okay, and then at point C, but before the bounce. Okay, so when we reached point C, that was over here. That was 2T plus T, that's 3T. Okay, so 3T is like here. Okay, so we've got that. And then the height of A and C. So the height of C is 32.98. So that's there, 32.98. And then these should pretty much line up. Yeah, that's good. Okay, and so that there is pretty much what they want you to show. Here are all the questions we're going to do, but I'm going to be splitting them up onto different pages. A wooden block of mass 150 grams is freely supported on brackets at a height of 2 meters when a bullet of mass 50 grams is fired vertically into the block as shown below. Okay, so you've got these supports over here, and then you've got a block resting on those supports, and then this bullet is going to be shot upwards into that block. Now, it says that the bullet embeds itself in the block and the bullet block system rise vertically into the air for a few seconds. Okay, so the bullet's going to land up in this block, and together these two are going to move upwards, and then falls back to its original position. First question, state the law of conservation of momentum in words. Alright, now whenever they talk about the law of conservation of momentum, they're referring to this formula over here. you know that the sum of the momentum before is equal to the sum of the momentum afterwards. So that's a bit of a hint as well for the next questions. But the actual definition is the one that says that, and I will show you the definition now, but it's the total linear momentum of an isolated system remains constant or is conserved. So there it is over there. The total linear momentum of an isolated system remains constant. And that's what we're seeing over here. The total momentum before the collision is equal to the total momentum after the collision. They said it remains constant. Okay, this one says calculate the magnitude of the bullet block system after the bullet becomes embedded. So once again, it's that formula, and I'm going to say upwards is positive. And now we're just going to go say, you could say mass of, so I like to just keep it all separate. So mass of bullet, velocity bullet, initial, sorry, that says bullet, initial, and that's velocity, plus mass block times velocity of the block, initial, equals mass bullet, velocity bullet, final, plus mass block, velocity block, final. Okay, so mass of the bullet, 50 grams. That's 0.05 because we have to work in kilograms. The velocity of that bullet before is 200. The mass of the block is 0.15 kilograms if you just divide by 1,000. And the velocity of the block before the collision is 0. It was just resting. Now the mass of the bullet is still going to be the same, which is 0.05. We don't know what the velocity of the bullet is going to be, and the block is still going to be 0.15. We don't know what its velocity is going to be, but the two velocities are the same because they are going to become one system. And so that is why you see that these two both have the same velocity. So some teachers are just going to combine the masses together and then have the velocity. Whether you do it like that or keep it separate makes no difference. Okay, now if I go type everything on the left here on the calculator, that's going to end up giving 10 plus 0 equals to 0.2 V. If I say 0.05 plus 0.15 V, I get that. Then if you had to divide both sides by 0.2, you're going to end up getting 50 meters per second. And we don't have to give a direction because they said magnitude. So that means that as this bullet embeds itself in this block, this system is going to move off at 50 meters per second. This question says, is the collision elastic or inelastic? For 4 marks, explained by using a calculation. So we know that if a collision is elastic, then the total kinetic energy initial is equal to the total kinetic energy final. And then if it's inelastic, then those two things are not equal to each other. So all that we go and do is we go work out the kinetic energy initial, and then we go work out the kinetic energy final, and then we see if they are the same. So remember that kinetic energy, it's going to be so the total kinetic energy is going to be the kinetic energy of the block plus the kinetic energy of the bullet initially. And so that's just going to be a half mv squared, or let's be a bit more specific and say that it's going to be a half times the mass of the block times the velocity of the block squared, plus then the bullet's kinetic energy, so it's the bullet times the velocity of the bullet squared. Because remember that kinetic energy is equal to a half mv squared. Okay, so if we had to go fill this in, we're going to have a half times the mass of the block was 0.15, its velocity was 0, so let's create a bit of space here, plus a half times 0.05 times 200 squared. And if we had to work this out, you should get 6,000 joules. Now we're going to go work out the final. So remember that you can either keep it separate or just put them as one object. So I'm just going to combine them as one object. So it's a half mv squared. So it's going to be a half times their combined mass, which is 0.05 plus 0.15, and their combined velocity, or their velocity, we won't say combined, we know that they both move at 50. And if we had to work this out, we get 250 joules. So look at the kinetic energy before, look at the kinetic energy after. Are they the same? No, they're not. So is it elastic or inelastic? We will say, therefore, inelastic. And then I think just to be safe, tell them why. As EK, or let's just say kinetic energy before, not same as kinetic energy after collision. Say before the collision. Okay. Right. And then this question says, on a different occasion, a bullet is fired closer to the wooden block at the same velocity, and it exits the block with an upwards velocity of 195. Okay, so you understand that when they fired the bullet from this distance, what happened is that the bullet didn't go out the block. The bullet got stuck in the block. Okay, but then when they decided to rather stand closer, because they're closer now, that bullet hit the block and then actually went out the other side. And they're saying that if the net force exerted by the block on the bullet is 5 downwards, calculate the time. Okay, so immediately, and they love to do this, by the way, guys, you must take note of this. Whenever they have these like question 4s where we first had to use the M1 V1 plus M2 V2, then later on in the question they often like to bring in force. And then what we do is we then begin looking at these formulas, okay, the ones that have F net, and check net F net. Okay, so let's go write down the formula. F net delta t, and they're also talking about time, right? And look, we have time, and that's equal to delta p. Now delta p we're gonna rather replace with mv final minus mv initial. You see, I just replaced it with that. Fantastic. Now what's important, a lot of learners do get this wrong, the net force exerted by the block on the bullet. So that means that we are working with the bullet, okay? So this is all about the bullet, is 5 newtons downwards. Why would the force be downwards? Well, think about it. This bullet ends up colliding with the block. What is the block going to do? Make the bullet go slower or faster? Slower. So it means that it must be exerting a force downwards. So you need to be careful now. A lot of learners are going to get this wrong because they're just not going to take direction into account. You can choose whatever you want. I'm going to choose upwards as positive because the bullet is going upwards. That just feels nicer for me. So that means that in the place of F net, I'm not going to plug in 5. I'm going to have to plug in minus 5 because they said 5 down. But we chose up as positive. Now delta t, we're not gonna we don't know what that is. Now remember, we are working on the bullet, so we're going to use the bullet's mass, even though the final oh no, that was the previous question, sorry. Even if the bullet was inside the block and it stayed there, if you were using this formula, you would still only use the mass of the bullet. You wouldn't use the mass of the whole system. So the bullet is 0.05. Its final velocity is 195, and then its initial velocity is still going to be 200, like they said. It says wooden block at the same velocity. All right, how easy is that, guys? We have everything we need. Now we just go type everything on the right-hand side. 0.05 times 195 minus 0.05 times 200. And that's going to give negative 0.25. And then to get delta t alone, we're going to end up dividing by that. And we end up with 0.05 seconds. Here are all the questions we're going to do for this one, but I'm going to split them up onto other pages. The first question says, well, let's first read here. An ice skater of mass 53 kilograms moves on a frictionless surface AB with a velocity of 6 meters per second. Okay, and then slides up a rough, okay, so this is a rough surface, until coming to a stop at point C, 1.5 meters above the horizon. The angle is theta. First question, state the work energy theorem. Well, remember, the work energy theorem is based on this formula over here. And so the definition is that the net work is equal to the change in kinetic energy. Let me get the proper definition. All right, so there you have two different options. Okay, so let's carry on. So this one says, draw a labeled free body diagram showing all the forces acting on the skater at point C. Right, so if that skater was at point C, then the different forces acting on would always be gravity. Now, back in the day, I used to break that up into parallel and perpendicular, but we're no longer allowed to do that. And then normal force always goes at 90 degrees to the surface. Then they said it's a rough surface, so there is definitely friction. And that would be it. Now, a lot of learners, if let's say they asked us to do the free body diagram over here, a lot of learners would be like, yeah, but sir, what about the applied force? There is no applied force. Remember that here you have this dude, his name's Johnny, and he was skating one day, and he decides to skate towards this point, and then he just floats up here, or like he just slides up here, and eventually he comes to a stop. There's no applied force. There's no one pulling him. There's no one pushing him. He's not even skating anymore. He's literally just skating along, and then he just decides to slide up here. Okay. Like the girls slide into my DMs. Okay, so that was a joke. Okay, so draw a labeled free body diagram showing all the forces acting on the skater at point C. Right, we've done that. And notice that it's for 3 marks, and we've got 3 arrows on the diagram. This question says, explain the term non-conservative force. Well, guys, we have spoken about this in detail already. Non-conservative versus conservative. And typically we've said that conservative forces are going to be gravity, whereas your non-conservatives are pretty much all the others. It's things like applied, friction, tension, things like that. Okay, but now the technical definition, they talk about path dependent or path independent. Okay, so what you must just remember, I'm not going to go into the details of that right now, but conservative, things like gravity, are not dependent. Well, let's actually just write in normal English. Don't depend on the pathway. What that means is it doesn't matter which way, like how the object goes. Whether the object goes like this, or whether the object goes just downwards in a straight line, or if it goes along a ramp like that, it doesn't matter. It's not going to affect the gravity. Whereas non-conservative forces, they do depend on the... Okay, that's all I'm going to say on that for now. We've spoken about these non-conservative, conservative in the past. And so here's the technical definition. It said, explain the term non-conservative force. A non-conservative force is the force for which the work done is dependent on the path. So that's what we said. Non-conservative, those forces do depend on the path, whereas conservative don't depend on the path. Calculate the angle of the slope if the skater experiences a frictional force of 20. Okay, so 2 main formulas that I would be considering here. I mean, you could actually probably go with a F net equals MA, combine that with a VF squared equals to V initial squared plus 2A delta X. But if you've watched some of my introduction videos on this, you would know that those 2, which we learnt about in grade 11, if you combine them together, then what we actually are doing is we're actually just using this formula. Did you know that these 2 combined give you that? Okay, so I'll prove it to you. If you expand W net, it's F net delta X cos theta, and then delta EK is a half mvf squared minus a half mvi squared. So check this out. F net, there it is. Delta X, there it is. Mass, there it is. Velocity final and velocity initial, there they are. All that's missing here is acceleration, but that is because there is acceleration in both, and so they almost used that to plug the one formula into the other. So whether you use this or whether you use this, It's the same thing. I don't want you to think of those as two like different methods. And then the other completely alternative option is to use the WNC formula. You can use whatever you like. They all work out. Okay, there's hardly ever a situation where the one doesn't work. I know that I do sometimes say that if the surface is curved, then I typically don't really use these ones, but they can work. There are ways to make them work, but usually when it's a curved surface, then I like to use this one. But if it's a straight surface, then I am happy to use all three. Yes, with experience, you will begin to think about like, okay, that one's going to work faster, but in most instances, they're all going to work. Okay. So yeah, for me, I mean, let's say I'm busy doing like a one-on-one lesson with a student. I let them decide which one they want to use. I'll never say like use this one or use this one, but like which one do I feel like using right now? I would say, okay, I know this. I know that to work out this angle eventually, I'm going to need to know this length. I'm going to need to know that length. But I mean, if I use this formula, I'm going to get that length. And if I use this one, when I break up the WNC, I'm also going to get that. So it's much of a muchness, guys. You can choose whatever you want. I'm going to go with this one. I'm just going to use that one. So I don't want you to think of those three formulas as different, like you can only use this one in that situation. No, that would be awful, guys. It's all interlinked somehow. Okay, so I'm going to use WNC equals delta EK plus delta EP. Now remember that the NC stands for non-conservative, and that only includes these. It doesn't include gravity. So what forces do we have? Remember we did a free body diagram, and we said earlier that there was friction, there was gravity, and there was normal force. Now, friction is definitely going to be included. I'm not going to include normal force because normal force is acting at 90 degrees to the direction that we are moving. And so even if you did have to include it in here, it's going to end up falling away completely. So the only force that's actually needed here is the frictional force. So we're just going to use the work due to friction. Okay. Now, remember, what is the general formula for work? It's force, distance, cos theta. So if you are doing friction, then what force do you think you should use? Well done. Friction. And then cos theta. Right. So I'm going to go replace that now with friction. Okay. And then I know that kinetic energy is a half mv final squared minus a half mv initial squared because it's the change. And then I know that potential energy is mgh. So I'm going to go mgh final minus mgh initial. Remember, the triangle means change, and change is always final minus initial. Now we're just going to go full stuff in. So, but this is where learners make mistakes. They're going to go put 20 as a negative. But remember, when you are busy with this formula, keep the force positive, okay? And then the distance is what we are trying to find. And now here's where things get interesting. So this angle, theta, is not the angle of the slope. I should have actually used a different angle, cos beta, for example. Beta, in that work formula, is the angle between the force and the direction of movement or motion. So the skater is moving up the slope, but friction is acting down the slope. So that's 180 degrees. So you're going to say cos 180. Now, did you know that cos 180 is minus 1? So that makes this whole term negative, which is what you want. But if you went and put the friction as a negative value over there, then you're going to get a negative here and a negative here, and you end up making it a positive, and suddenly this dude is speeding up because of friction. Doesn't make sense. So yeah, just look out for that. And then, okay, now we're going to go full in the mass. This guy is 53. Final velocity 0, because at point C, they tell us that he comes to a rest, to a stop. Okay, initial velocity is the velocity at point B, which would be, goes along a frictionless surface AB with a velocity of 6. So the velocity along this whole section is just 6. It stays the same. So at B, it's also going to be 6. So that's the initial velocity. Remember, we're only looking at this piece here. Sorry, up to the top. That is the part of this question. So this velocity here is also going to be 6 squared. Now mass 53, gravity is always 9.8. What is the height over here? It's 1.5. What is the height over here? Well, it's 0. It's on the ground. And there we go. Now it's just a case of plugging things in. So if you type that on your calculator, that's going to give you negative 20. So negative 20 delta x. And then on this side, you can go type in all of that on your calculator. But keep in mind, this part here is 0, and this part here is 0. So if you want, you can just type that on your calculator. Don't forget that negative. And so that's going to eventually give you negative 174.9. Then we divide both sides by negative 20, and we should end up with a final answer there as 8,745. I'm not going to round off. Right, so now we have this distance, 8,745. So now we can use trigonometry, because now we have the hypotenuse and we have the opposite. So remember SOHCAHTOA from grade 10. So that's going to use sin. So the sin of that angle is the opposite, which is 1.5 over the hypotenuse. And then to get the theta alone, you're going to end up saying shift sin. So you're going to press shift on your calculator, and we get 9,88 degrees. An observer with a detector standing on the side of a straight road records the frequency of a police car siren moving in a straight line on 2 separate occasions. The police car moves at the same constant speed. Okay, guys, I have a crazy story. I wasn't sure if I wanted to share this one, but I'm going to do it anyway. So this weekend, this last weekend, it was my birthday. 7 September is my birthday, so 6 September, Saturday, we go out, right? And I'm busy driving. I've got 3 of my friends in the car. We're on our way to like the venue where my birthday party is going to be. And so I have a sports car, okay? And there's something that I love doing, and that is whenever I have to do a U-turn, instead of like doing like a turn, reverse turn, I just, I put my car into sport mode and I literally just do a donut. Not a full donut, just a 180, but it's quick, okay? I've done this with like all my friends in the car, and I do it a lot, okay? I've even done it like in Cape Town main road, like during the rugby, there were tons of cars, and I just, and I do a quick donut because it's just much faster that way. Anyways, I did this stunt again the other night, and I do it, I park my car, and I go into the wine bar, and I sit down, I order my drinks. Suddenly the bartender comes to me, taps me on the shoulder. He's like, or she's like, Kevin, there's police outside looking for you. And I'm like, no. I did tell her, okay, I did do an aggressive like U-turn now. And she's like, yeah, they waiting for you. So I go outside, 3 police cars are parked there. I walk up to the police car, and the driver, he starts shitting on me. He's like, what the F do you think you are doing driving like that, putting other people's lives in danger? Who do you think you are? And absolutely slaughtering me, guys. Like, I felt so small in that moment. Then the passenger of the vehicle, he takes me to my car, and he asks for my drivers and stuff, and I could see he was a lot more patient and friendly. And he said, listen, that man, the driver, he's my senior. Don't mess with him. He is very intense. So anyways, we then walk back to the police car where they write out my ticket and all of that. And the main driver again, he starts absolutely launching on me. He's like, who do you think you are doing that with your car, putting other people's lives in danger again? And I started smiling because I was feeling nervous. And he's like, wipe that effing smile off your face. He then talks to the passenger, the other policeman. He's like, kyk daarso op die system, or look on the system. I want to see if this young chap has any warrants for his arrest, because I would love to put him in cuffs tonight. And I was like, jeepers, this guy's being aggressive. Anyways, luckily there weren't any warrants or anything against me on the system, and I just ended up getting a big fine, and that was it. But yeah, guys, what got me onto the story? Oh, police car. So yeah, literally, that was 3 nights ago or 4 nights ago. yeah, I'm a bit naughty on the road sometimes, if I'm very honest. I know I'm supposed to be like an example and stuff, but since I was a kid, like I've always had a thing for cars. I love cars. And yeah, I'm a scientist. Like I know how to do a quick U-turn without having to do a 3-point turn. Ain't nobody got time for that. Anyways, that's what happened. Okay, so hope my mom doesn't hear this. Right, so the first question says, state the Doppler effect in words. Well, let's first, I feel like I didn't finish. The police car moves at a constant speed. The results are shown. Okay, so they give us these two graphs. Boom, boom. Okay, and now it says state the Doppler effect in words. So what is the Doppler effect? The Doppler effect is all about that whole, like, if an ambulance is moving towards you, you're going to hear a high frequency. If it's moving away from you, you're going to hear a low frequency. So that's what the Doppler effect is all about. So let's get the definition. So here we have it. It's either going to be the change in frequency of the sound detected by a listener, because the sound source and the listener, that's not really the one I normally use. I normally use something similar to this. It's a change in frequency as a result of the relative motion between source and an observer. They are very interested in the underlined words, okay? That's what they're really looking for. Right, this one says, which graph A or B shows the police car moving away? Okay, so what we need to remember is that, let's say you are standing on the side of a road and there is a vehicle with a siren. Woo, 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 woo. That's meant to be a siren. Goodness me, Kevin, what are you doing, my guy? Okay, let's just say like that, and then of course the car has wheels. Okay, and the car's moving that way. My drawings are so bad, I have to make sure people know which way the car's going. So if a car's going towards you, then obviously these sirens are giving off waves. But because it's coming towards you, these waves are being squashed together. You can almost think of the car and the person causing the waves to be squashed. And so there's going to be a lot of waves reaching this person's ear per second. So the frequency is going to be very high. However, if the car was going the other way, then what happens is that the waves that are given off, they become more stretched out. And so there's going to be less waves reaching this person's ear per second. And so the frequency is lower. So when the objects are moving towards each other, frequency is higher. When the objects are moving away, frequency is lower. Now, personally, I think there's a mistake in this question, because I think what they did is they wrote this FO, which is the frequency that the observer hears. That isn't meant to be there. That isn't meant to be there. That is meant to be there, and that is meant to be there. So that is what the detector is measuring. It measures 1,100, and then the detector measures 900. The dotted line is the police car. That is what the police car's frequency actually is, and that doesn't change. The police car's frequency stays the same, but the observer, or the person who is measuring, that is going to change based on whether the car is coming towards the observer or away. So this observer is the same as your listener. It's what the listener is hearing, whereas the police car, well, that is the source. That is the source. So the dotted line is the source. And I looked at other, because I was very like, what is going on here? And then I looked at other YouTube videos of other creators who have done this question, and no one mentioned it. So quite weird. So the question says, which graph A or B shows the police car moving away? Well, we know that when objects move away from each other, or when an ambulance is driving away from you, the frequency that you are going to hear is going to be less than what the ambulance is actually making. So this is going to be the correct answer, because here's what the police car is actually making, and then here is what the observer is actually hearing. So you can see that it's less, what's below the dotted line. So we are going to say that it is graph B, and then it says give a reason for your answer. And the reason is going to be because the observed frequency, so that's this one, is lower than the source frequency, which is the actual police car siren, which is that one. Okay, moving on to 6.3, calculate the speed of the police car. Now, it's for 5 marks. Now, normally when they have two scenarios like this, one going towards, one going away, then it's usually going to end up being simultaneous. So we know that the equation for Doppler effect is like this. Okay, where this is the listener or the observer, this is the source, so this is the police siren itself. This is the speed of sound in air, which is normally 340, and they've also asked us to keep it as 340. This is the velocity that the listener is moving at, and this is the velocity of the source, which is the police car. So let's first do, we know that this one is the towards, and this one is when they are moving, or when the police car is moving away. We know that when things move towards each other, then the observed, the frequency that the observer or the listener hears is going to be higher than the actual source, which is the police car. And so for that one, we know that the top is a plus and the bottom is a minus. That is how it works when things are moving towards each other. Okay, this is for graph A. Now, the frequency of the listener for that one is 1,100. Okay, the velocity of here is 340. Now, this next part's a little interesting. So, some learners are starting to experience something quite interesting in class where some teachers, if you fill in a 0 here, they mark you wrong. It's quite interesting to me because technically the velocity is 0 of the listener, and so I would normally just go like that. But what some teachers are now doing is they're just marking the learners wrong if they do that, which is quite interesting. So I'm going to leave it like that, and then I want you to check what your teacher's doing, okay? Because it differs. And then, okay, now the velocity of the source, we don't know, so we just do it like that. And then, so they don't want to see you putting the plus 0 here. They don't want to see that. So, and then the frequency of the source is, we also don't know. So you see how there's two unknowns, but that is okay because we are going to be doing simultaneous. Now over here, let's do the frequency, or let's do the graph B. So now the objects are moving away from each other, so we're going to use a minus at the top and a plus at the bottom. Okay, now the frequency that the listener hears in this scenario is 900, and then it's going to be 340. Now once again, I would normally have said minus 0, but I'm noticing that some learners are now getting penalized if they are doing that, which is something I haven't seen before. So I'm rather going to play it safe, but you need to just check with your teacher as well, okay? And then we're going to say 340 plus Vs times Fs. So what we can see is that we have two unknowns, two equations. Now, the way that the best way to equate these things is to get the Fs alone here and to get the Fs alone here as well. Now, to create more space, I'm going to delete all of this, but just remember that the point of this question is to calculate the speed of the police car. So we're trying to find Vs. That is our ultimate goal. Okay, so if we take this equation, how do we get Fs by itself? Well, what we're going to do is we're going to leave it here, and we're going to take this up to the top and this down to the bottom. So we're going to end up getting 1,100 multiplied by 340 minus Vs over 340. Okay, now I'm going to do the same with this one. So it's going to be 900 multiplied by 340 plus Vs over 340 equals Fs. So now I can equate these two expressions, and so I can say 1,100 times 340 minus Vs over 340 equals 900. I'm going to take that x away actually and just put it in bracket. Okay. And so what happens is that these 340s can cancel, and so what we're now going to do is just multiply the 1,100 into the brackets. And so we're going to end up with 374,000 minus 1,100 Vs equals to now 900 multiplied by 340 306,000, and then plus 900 VS. Okay, I'm going to take the VS's to the right, and so you're going to end up with 900, that, and then on this side you're going to end up with, and so it's 2000 VS equals to 68,000, and then if you divide both sides by 2000, you get 34 meters per second, and that is the velocity of the police car. Study the emission spectra A, B, C of a distant star as observed from the Earth. Spectrum A is the laboratory reference, okay? And then first question says, which spectrum indicates that the star is moving away? Right, so we've spoken about this before, where we've got this red shift happening, where scientists are able to observe that the universe is expanding. I've made videos on this red shift and how because the frequencies that stars are giving off is becoming more and more red, like the red frequency, what scientists are observing is that the Earth is expanding. So if this is the reference, then which of these shows that we're going more towards the red? Remember, red is on the left, blue is on the right. So if you look at these lines and these lines, you want to see them going more towards the left. So here you can see that they have shifted left. Can you see that these two are now here, these two are now here, and like this one is now there. So these lines have shifted left, and so they've gone more towards the red side. So which spectrum indicates that the stars are moving away? B. I'm not going to go into all the details now about red shift, blue shift. I have made videos on that. Now, if the blue part is observed, describe the frequency and wavelength. So what we need to understand, you know how we've got the different colors, red, orange, yellow, green, blue, indigo, violet. We know that red is very chilled. It's like super relaxed, whereas violet is intense. Okay? So, and then as you go towards this side, it becomes more intense. So what we can say about red, whereas violet has low wavelength and high frequency. Now blue is closer to this side, okay? It's more on the high frequency side. So all you're going to say here is high frequency, low wavelength. Here are all the questions we're going to be doing in this question, but I'm going to be splitting them up onto individual slides. 2 point charges, A and B, are placed 3 meters apart. The charge on A is that, and the charge on B is that. P is a point 1 meter to the right. Okay, first question, define the term electric field. Right, when they ask for definitions, very often looking at the formula really helps. So there are 2 formulas that we have on our formula sheet for electric field. Here they are. Now with the definition, this is the one you want to look at. Okay, so I'm going to give you the proper definition now, but it goes something like this. The electric field at a point is equal to the force experienced per unit positive test charge. So it's the force experienced per unit positive test charge. So this is charge. So you see how we can get the definition straight from the formula. So let's go get the formal definition. And so there we have it. The electric field at a point is the electrostatic force experienced per unit positive test charge, or sorry, they didn't say test charge, per unit positive charge placed at that point. So what's important is that you do include the word positive and that you also remember that. Remember that, guys. Whenever we are dealing with questions later on, or in these kind of questions where they're going to have a random little point P, some learners are like, yeah, but sir, I don't know, should we pretend that this is positive or negative? Well, I don't know, Bob, you tell me. It's in the definition. Okay, so that's that. Now, this one over here says, calculate the net electric field at point P. Right, now, remember there are 2 formulas for electric field. Now, in these kind of questions, we're going to go rather for this one. So, what we need to understand about that formula, well, actually, no, we don't even have to, they just want it at point P. Now, some learners get confused. They're like, yeah, but sir, what is P? Is P a charge? No, P is just a random place, but we are going to assume that it is a positive place. Okay? but it's not a charge. It's just a point, and we are just going to pretend that it is positive. Why? Just to make our calculations the same as Mr. Rajesh, who might be doing this question in India. Maybe you are two scientists one day, and one of you is living in, I don't know, Hawaii, and the other one is living in India. Well, you guys need some common ground. And so what scientists around the world decided is, hey, let's pretend that let's pretend that these point charges are positive so that our calculations are all relative to that. Guys, look how easy this is. This is easy marks. All we're going to do now is realize that point P is just a random little place. Now, point P is chilling there, and it's like, ooh, I can feel there's some kind of electric field around me. I wonder where it's coming from. Well, guess where it's coming from? It's coming from B and it's coming from A. So what we need to do is work out the combined effect of those two on this one. So how do we do it? Well, first step, choose one of them. Let's say you chose A. Then I want you to completely ignore this one, pretend that that one doesn't even exist, and just go work out the effect of A on P. Okay? So the way we do that is we use this one. Kevin, why aren't we using this formula, my guy? Okay, well, listen. That you would only use if they talk about electric force. But we are talking about electric... Well, if they say electrostatic force, then we do this one. But if they're just saying electric field, well, then it's just this one. Okay, so let's go work it out. So we're going to go E equals 2. Now, K is a value on your formula sheet. It's a constant, 9 times 10 to the 9. Now, what is the value of Q? Well, we're busy with this one, so it's going to be 6 times 10 to the negative 6. What is the distance between that and that? Well, that's 4 meters, because that's 3 and that's 1. So if you add them together, you can use your calculator. Let me quickly whip out my calculator, put it into stats mode. 3 plus 1. Calculator is giving me an error. It's 4, guys. Okay, so we're just going to go 4 squared. All right, now you just go work this out, and that's going to give you 3375. Now the units for electric field is Newton per Coulomb, so we go n.c negative 1, and then now we've got to think about the direction. Now this is why it's important to know that this is taken to be positive, because now we know that when this is positive, and if this one is positive, what do they do? Well, like charges repel. So what does that mean? Some learners get a bit confused. Well, it means that A is going to try push this one away. So it means that it's going to push P to the right. So the effect is going to be to the right. Now we just go do the exact same thing with B. So now we just forget that A ever existed, and we just go and work with B now. So let's just remind ourselves that this was for A, and now this one over here is going to be for B. So same formula, of course, and we're going to then go 9 times 10 to the 9. Now remember, don't put the negative on the calculator with these formula. Don't put the negative in the formula. We just leave it as a positive, and then the distance is 1 squared. And the reason we don't put a negative is because charge is a scalar. It's not a vector. It has magnitude, but it doesn't have direction. Okay, a charge can't have a direction. Sometimes a charge is negative, like we see here, but that's just because it's got excess electrons. But it's not because of the fact that it's chilling to the left. It's just a charge. Okay, and then, right, we're going to go put all of that in the calculator. And that's going to be 27,000. Now we're going to say Newton Coulomb again. Now we've got to look at the direction. So remember, this one is now negative. This one is now positive. What do opposites do? They attract. But now think about that carefully. That means that P is going to be pulled left. Okay, so what we have found is that A is obviously going to try cause P to go right. B is going to cause P to go left. And so now we just need to somehow find a combination. And so you can go work out the net effect of those two. I'm going to choose to the right as positive. So that means I'm going to take this one as, well, A as a positive, because it is to the right, and then I'm going to say minus the effect of B, because B is to the left. It's literally like F net equals MA almost. And so, like, same thing with forces. We're just choosing directions now. And so the net effect is going to be 3375 minus 27,000. 1000, and that's going to end up giving negative 23625 Newton Coulomb, and so therefore it's going to be or let's just say E net is going to be 23625. Okay, that's going to be a little bit squashed. 23625 Newton Coulomb, and we're going to say left. Okay, so we now know that because of A and B, the combined electric field is that, okay, which is what we worked out in the previous question. Now it says that a proton, which is positive, is placed at point P. Calculate the magnitude of the initial acceleration of the proton if that is its mass. Guys, this is super easy. Let me explain. We know that the other formula for electric field is this one. So, and we know that here's force, and we know that force can also be equal to, or F net can also be equal to ma. And that is how we are going to get acceleration. Think about it. We've just worked out E from the previous question, so we have that. When you use this formula, then the difference is this Q is the charge of the object at that place. Okay, so they're saying that a proton is placed at P. So we know what the charge of a proton is. How do we know the charge of a proton? Well, we know the charge of an electron. They give us that on the formula sheet. It's 1.6 times 10 to the negative 19, but it's negative because it's an electron. A proton is the exact opposite. A proton is just the positive version of an electron, right? And so we have this. So can we work out F? Yes, we can. Once we have F, we can come plug it into here because we have the mass. And so check this out. We can get A. You see that, guys? Not bad, hey? Guys, it is, what's the time now? It's 5:45 in the morning. I'm quickly trying to finish this exam paper because you guys need this exam paper literally by like this afternoon. But I'm about to have my first sip of coffee. Ooh! You have no idea. It's got like there's a bit of a coldness in the air this morning. I'm sitting here, but I'm so like silly. It's cold, but I don't have my socks on. And my feet are freezing, but I get so hooked into my recording that I forget to go put socks on. Yeah, I've always been like that. If you're wondering, the coffee tastes really nice. Okay, so let's actually go do this question now. Let's go tackle this bad boy. Okay, so, right, so we're going to start with this formula over here. So, oh, just by the way, you know how I said that when we use this formula, then this charge here is the charge at that particular place. But then earlier in question 7.2, we used this one. And then notice that with this formula, this Q, notice that it's a capital, whereas this one is a small letter. This one is the charge creating the electric field. So remember in that question, they wanted to know what is the electric field over here. So then we used these two because they are the ones that are creating the electric field at that point. But then when we use this formula, it is the actual charge at that point. Okay? But in question 7.2, you can't use this formula because we didn't have anything at point P. We just had they just said it was a place. Now in question 7.3, they have actually put a charge there. Sometimes they use an electron, then you would use this one, and then but you still wouldn't put the negative in the formula, but it would affect your sign at the end. And then but now in this one we're using a proton. Okay, so we know that a proton is positive, and we know that from question 7.2 we also knew that we pretended that this was positive already. So if this thing is positive, then the electric field goes to the left. If they used an electron instead, then it would switch that to the right. Okay, so I'm going to choose left as positive so that when I plug E into this formula, I can leave it as a positive. Okay, and then the force, we don't know what the force is, but we do know the charge. It's 1.6 times 10 to the negative 19. And so if we now had to go and take this part and multiply it up to there, we're going to end up with a force of 3.78 times 10 to the negative 15 newtons. And that's going to be to the left because we got a positive answer. Okay, and so now we have the force. Now, with F net, technically that means we got to look at all the forces acting on P, or this proton that is here. However, in the horizontal direction, there are no other forces except the combined effect of these two, which we've just gone and worked out through this. And so the F net is also going to be, I'm going to choose left as positive again. We're going to choose 3.78 times 10 to the negative 15. The mass is 1.67 times 10 to the negative 27, and then acceleration. So to get A alone, we're going to end up saying 3.78 times 10 to the negative 15 divide 1.67 times 10 to the negative 27, and we should get an acceleration as, to two decimal places, 2.26 times 10 to the 12. And, oh, they just want the magnitude. Okay, so we don't need to give direction. So we can just say meters per second to the negative. If an electron was placed at point P instead of a proton, how would the acceleration compare? Now be careful. Remember that the charges are the same. So we can imagine that from this formula over here, this value wouldn't change. Well, obviously it would just be the opposite sign because an electron has an opposite charge. This would just still be 1.6. Remember, we don't put the negative in on this formula, so that would still be 1.6. Even, yeah, because remember, an electron is this one, but we won't put the negative in the formula. But we will change the sign for that one. And then this stays, this question says, if an electron was placed at point P instead of a proton, how would the acceleration of the electron compare to that of the proton? Well, let's look at the two formulas that we used for the proton, and then let's try to analyze. So if we had to use an electron here, then this value, we would still use this, but we would just put it as a negative. Assuming we chose left as positive. So you would have to take that into account. This, you would still keep it as positive 1.6 because we don't put a negative in that place over there. And then you would get the same value for F, the same magnitude, but the direction would just be different. Then when you drag that F value over here, remember that it's the same magnitude that we got earlier. But now we would have to keep in mind that the mass of an electron, it is almost negligible. Remember, we often say that a mass of an electron doesn't really exist. Of course, there is a mass, but it's so small. So think about if we had to solve for A, then if this value here is extremely small, then it's going to cause this entire thing to become extremely large. So that acceleration of the electron is going to be much larger because it's got the same force acting on it, but it's a much lighter object. So when that force acts on it, it's going to accelerate like crazy. All that you need to say is that it's going to have a larger acceleration, and it's also going to be in the opposite direction. Okay, so it's going to have a larger acceleration than in the proton, and it's going to go in the opposite direction because remember, an electron has the opposite charge. I will be splitting these questions up, but here are all the questions that we're going to be looking at. Let's begin. A battery with an unknown EMF and an internal resistance of 1 ohm is connected to 3 resistors, boom, 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 and a light bulb, which is this one over here, and a high resistance voltmeter. So that's probably this one here, or it could actually be that one there. It doesn't really matter. A switch and an ammeter. The resistance of the light bulb is 4 ohms, and the resistance of the 3 resistors are 2R. Okay, so that doesn't mean 2 ohms and 1 ohm and 6 ohm. That just means we don't know the value of R yet, and so they're giving it to us in terms of a variable. Perfect. Define the term for the first question, EMF. Well, you know those formulas that we used to use like in grade 10 I equals to Q over T, V equals to W over Q. Well, this is voltage, which you can think of as EMF, and you can actually get the definition of it from here. It's going to be something to do with EMF is the maximum energy given per charge or something like that. And so there we have it. It is the maximum energy provided by a battery. So it's energy of the battery per unit charge passing through it. All right. And so let's now move on to this one. When the switch is closed, okay, so the switch is closed, the current through the ammeter is 0.2 amps. Okay, there we go, like they've showed us. And the potential difference across R1 is 6 volts. Okay, R1 is 6 volts. Write down the value of V2. Okay, so the way you got to think about this is actually not an easy question for 1 mark, but all you're going to do, forget about everything in the circuit. Forget about everything and just focus your attention over here. And I want you to imagine how these electrons are flowing. Okay, so that some of them are going to go, this way, and some of them are going to go this way. Okay, now just focus in on the ones that are going this way. Can we agree that this part of the circuit is in series? So the current that is going to be able to flow through here is exactly the current that is going to flow through here. Okay, so now we can just look at this. This one has a resistance of 2R, but this one has a resistance of R. So if we just go look at the formula, V equals to I times R, we can see that the voltage then, if this is a constant for both, because we said that the current here is going to be the same as the current here, then we can see that the voltage is actually just going to be proportional to the resistance. So if this one has a resistance of 2R, then the voltage was 6. Then if this one has a voltage of, if this one has a resistance of R, which is half of that, then its voltage must be half because they're proportional, which means that if the resistance goes up, the voltage goes up. And if the resistance goes down, the voltage goes down. That's what directly proportional means. So if this one has a resistance of 2R, and this one is then R, it means that this one's resistance is half. So it means the voltage is going to be half. And so it's going to be, instead of 6 volts, it's going to be 3 volts. Right, so now what we can do is we can look at the total resistance of this one. So this one is going to be 2R plus R. So total resistance in this branch over here is going to be, let's say, top branch. We don't have the values, but it's just going to be 2R plus R, which is 3R. Now the total resistance in the bottom, well, that's just 6R. Okay, so now think about this. If you are an electron coming this way, which pathway would you prefer? Would you prefer to go down the pathway that has a resistance of 3R, or would you rather go through the pathway that has a resistance of 6R? Well, if you're a normal electron, you're going to choose the path of least resistance. So most of the electrons are going to go this way, and then the rest will go this way. Now, if you look at the ratio, it's 3 and 6. So it means that the amount of electrons that are going to go this way will be double the amount of electrons that go this way. So the current in this path is going to be double the current in this path. So if this path is 0.2, then the current in this path is going to be 0.4 amps. And we said that the current in this pathway here is going to be in series. So if it's 0.4 over here, it's going to be 0.4 over here, and it's going to be 0.4 over here. Okay, so it's exactly double that one. This I can imagine actually threw a lot of learners off. And I don't blame you. It is a little bit different to the way that they would normally ask it. Okay, so we now know that we have 0.4 amps flowing through the top branch, and we've got 0.2 amps flowing through the bottom branch. We also know that this is 6 volts. So now it says calculate the resistance of R3. Right, now what we must remember when you have parallel branches, what is the same? Is the current the same in parallel? No. We need to remember that in parallel, voltage is the same. But what do we mean by that? Well, what we mean is that the total voltage of of this branch is the same as the total voltage of this branch. So in the top branch is 9 volts. How did I get 9? Well, this is 6 and this is 3. So you just add them together. And now we said that in parallel, voltage is the same. So therefore, bottom branch must also be 9 volts. So now we have 9 volts. So now for this device over here, because that is the only device in that branch, we don't look at the ammeter, that just measures. We've got the current and we've got the voltage. So then we could say I equals to V over R, and we could get R alone. So you would eventually end up with V over I. And so the voltage is 9. The current is 0.2, and so that's going to be R is equal to 45 ohms. This question says, and remember guys, we still have more questions coming up, one more. So it says calculate the value of the EMF. So the main formula we have on our formula sheets is this one over here. And so let's see what we have. We can easily get the current in the main circuit, because we know that in this branch there's 0.4 amps, in this branch there's 0.2. So then how much current do you think we have in the main part of the circuit? Well, that would just be those two added together. So in the main part of the circuit we have 0.6 amps. And then what happens is that when it gets here, 0.4 goes that way and 0.2 goes that way. It's just like water flowing through a river. If you've got 0.6 liters of water and then 0.4 goes around that rock, then 0.2 has to go around the other side of the rock. It's simple, me bro. Okay, so then we've got that. Now, we've got the internal resistance of the battery, but what we don't yet have is the total resistance in the circuit. So we need to take into account this branch, and then this one over here. So the first thing is, we did calculate R3. We got it as 45 ohms. Okay, so 45 ohms. And what that 45 ohms was 6R. So what we can say is that 6R is the same as 45. So if you then had to divide by 6, you get 7.5. So R is 7.5 ohms. Not this R. Ooh, that's going to cause confusion maybe. That's not that R. That R over here is just the R that they put on the symbols. So this R is 7.5. This is going to be 2 R's, and so that's going to be 15 ohms. And then this is going to be, that's already in ohms. Okay, cool. So we could go work out the top branch resistance. We just add these two together. So that's going to be 15 plus 7.5, which is 22.5. I know a lot of you are wanting to use parallel formula, but you can't use parallel with that, and that. We first have to combine this branch's resistors into one, which we've just done over here, and then we can use parallel. So remember, this formula is given to you guys on your formula sheet. These two branches are in parallel. So we're going to go 1 over top branch, which is 22.5, plus 1 over bottom branch, which is 45. And so now we end up with 1 over R parallel equals to 1 over 15. Then we flip both sides over. Okay, so the parallel branches are going to be 15 ohms. So now what you can imagine is that the circuit, this part now is just one big resistor of 15. And so that big part is in series with that part. And so you could now say 15 plus 4, which is 19 ohms. And so R, but now, you see, I don't know why they do this in the exams. So now this R, which is now this one, not this one, is going to be, well, let's just say R total. You know, if I had to set exam papers, I would take all of these little things into account, because these little things, like causing that little confusion, it's not really fair on students, in my opinion. It's not really testing understanding. It's just being a bit silly. Anyways, so we have this R now, and so now we can go work out the EMF. So EMF is equal to the current, which we said was, I'd be freaking out if I was in a test right now and I forgot where I wrote it down. There, 0.6. Okay, 19 plus, and then the internal is 1. Okay, so that's going to be 0.6 times 20, which is 12 volts. In a separate circuit, a variable resistor is connected to a battery, so here's your battery over here, with an unknown potential difference as seen in the following diagram. So a variable resistor, it's just a resistor that can change resistance. So they can press a button and then it just changes the resistance. Okay, the graph below shows the relationship between the power and the resistance of the resistor. So it's 1 over R. Use the graph to calculate the potential difference. Okay, so we know that there's 3 power formulas that we have. P equals to that, P equals to that, and P equals to that. Okay, so we can see that on the y-axis we've got power, and then on the x-axis we've got 1 over R. Where do we see 1 over R? Well, that's going to be this one over here. So P equals to 1 over R. You can think of it as 1 over R like that, and then you can put the V squared in the front. Okay, so if you think about a straight line, it normally has the formula y equals to mx plus c, but we don't have the plus c part because the c, which is your y-intercept, is 0. So I want you to now make a comparison of this. So we've got y, which is now p. And then we've got x, which is now 1 over R. So that means that the gradient must be v squared. I'd rather do that in a different color. So v squared is the gradient. And so now we can literally just go work out the gradient. How do we work out the gradient? Well, it's a straight line. So you just use... Now some learners are like, oh, analytical geometry in a physics paper. I'm dead. I'm going to go comment about this on TikTok afterwards. Guys, they're often going to throw in little things from different sections, but it's never going to be super critical. Okay, so let's go work this out. You can use any 2 points. I'm going to use this one, and I'm going to use this one. Okay, and so we're going to go use, so we know that gradient is y2 minus y1 over x2 minus x1. And so that's going to be, I'm going to use this as point number 2, and this is point number 1. And so it's going to end up being 1,000 minus 0 over 10 minus 0. And that's going to end up giving us 100. So that means that v squared, which is the gradient, is 100. And so therefore, v must be 10 volts if you square root both sides. So, and v is potential difference. I will be splitting these questions up onto individual pages, but these are all the questions that we are going to be looking at. The first question says, is this an AC or DC generator? So all that you do is you just go and look at these devices over here. Either it's going to be a solid circle, or there's going to be a split, and it's going to look something like that. Okay, I don't see a split, I can see full circles, so that means it's slip rings, so that's going to be AC. And we're going to say slip rings. Or we can say that you can see slip rings, or it has slip rings. You want to say slip rings again, Kevin? We get the point, my guy. Okay, 9.2, state the energy conversion. So when you have, in grade 12, we learn about 2 main things. We learn about motors, and we learn about generators. Now, generators, you have to rotate them. That is called mechanical. And why do we rotate? What are we trying to do in a generator? Why does Eskom have generators? To try and generate what? Electricity. So the rotating converts into electrical. If you have a motor, then you already have the electrical, but then what are you trying to do? You're trying to cause rotation. Okay, so state the energy conversion for a generator. You're just going to say mechanical to electrical. In which direction will the induced current flow? Okay, so this is where we have to use the what? Left or right? What would you say? It's the right. Remember, with a generator, we always use the right hand. With a motor, we use left hand. So you're going to take your right hand, and your first step is you're going to take your index finger, which is the one next to your thumb, okay? And you're going to point that from north to south. So you're going to your index finger is going to be pointing in this direction right now, okay? With your right hand. North to south. Then your thumb, okay? Now they're talking about AB. AB is this one over here, and we can see the direction of rotation is like that. So what is AB about to do? Is AB about to go up, or is AB about to go downwards? AB is about to go upwards, right? So then your thumb should be pointing upwards, and then look at your middle finger. Make that 90 degrees to your index finger. what direction is your middle finger pointing? Is it pointing more from A to B, or is it pointing from B to A? If you've done it correctly, it should be pointing from A to B. So we're going to just say A to B. The diagram below shows the EMF time graph for one complete rotation. This question says, calculate the resistance RL if the value of IRMS is 4,55 when the Vmax is 150. Now, I know you grade 12 students. This section usually comes towards the end of the year, and I know right now that if you're watching this, you might be feeling a little bit about this section and all these calculations, right? So let's just go get the formula sheet, and I'll try to help you to just plug and play. Okay, so here's all the different formulas that we have available to us in this section. But now you'll notice that there's no real formula for R. And so what we must remember is that if you rearrange I equals to V over R, then R is always going to be V over I. Now, what V and what I do you use? So here's how it works. If you want to use the maximum voltage, then you also use the maximum current. If you rather want to use the RMS voltage, then you must use the RMS current. So as long as these two match, you're good. And please note, for R, you don't get a R max and a R RMS. You don't get this, and you don't get this. With resistance, it's just R. Okay, so you can choose whichever one you want to use. You'll notice that, either we're going to have to change this or either we're going to have to change that. So I'm going to change this one. So I'm going to use this formula over here. So VRMS equals to Vmax over 2 and square root 2. And then that's going to be 150 divided square root 2. And then I'm not going to round off. Okay, and that's going to be in volts. Now I can go and use this formula over here. That's going to be that divided by that. And then that will give us an answer of 23.31 ohms. Okay, they tell us that the load is now replaced with a bulb. Okay, so the load is now replaced with a bulb with a power consumption of 400. Assume that the bulb, when they give you this power consumption, that power consumption is the average power consumption. Unless they say it's the maximum, it's the average. Assume that the bulb is 100% and calculate the energy emitted by the bulb in 3 minutes. Now, when it comes to energy, we can start thinking about these formulas because the W is energy. All of those W's are energies. But the only issue is that they don't give us these formulas in terms of these RMS and all of that. So we just got to keep that in mind. Okay, so they say that we have a power of 400 and okay, so we've got power, we've got energy over here, so that's what they want us to, is that what they want? Assume that the bulb is that, calculate the light energy, yes, okay, and then we need time. Okay, so we actually have everything that we need. So the power is 400, the energy is what we're looking for, or we should always write our formula down. And so the power is 400, the energy is W, and then time must always be in seconds. So that'll be 60 times 3, which is 180. And so if you had to then multiply these two, you end up with 72,000, and energy is measured in joules. Okay, now this one says the speed of rotation is doubled. Okay, redraw the above diagram in your answer book on the same set of axes. Include the old new pattern obtained. Okay, so they want us to redraw this if the speed of rotation is doubled. So there's going to be two things we need to keep in mind here. We know that the EMF in a generator is dependent on these factors over here. Now, they're not changing the number of turns. However, what they are doing is they are they're doubling the speed at which this thing rotates. So if you double the speed at which something rotates, what are you going to do to the time that it takes to make one complete cycle? Are you going to double that, or are you going to half that? You're actually going to half that. Think about that carefully. When you do something faster, the time goes down. Okay? So what happens is that these cycles are going to become half the length. So instead of only being able to do one cycle in 0.2 seconds, you're now going to be able to do 2 cycles in 0.2 seconds. And this value is going to actually double, because when you half the denominator, you end up causing this value to double. So the peaks are now going to go up to 300 and down to minus 300. So you got to try draw that now. So it's going to go up to 300, down to minus 300, sorry, down here, and then you're also going to have to fit 2 instead of 1 in that same time span. Okay, so here's the original. Now the new one's going to go up to 300 and down to negative 300. Okay, and it's going to complete one whole cycle by the time we get there. So halfway is going to be there, and then it's going to, wait, this is quite interesting. Oh no, halfway is going to be there, and then it's already going to have to reach there. Okay, so your graph's going to look quite narrow. It's going to go like that, and like that. And then you can actually just draw 1, but I checked on the memo. If you do decide to go and draw 2, they don't penalize you for that. Okay, so because they didn't really say how many they want us to draw, but things that you should include, you should put 0.1 over here, and then they did say label the new pattern B, so let's label that pattern as B. All right, and so that's how you would draw that. And then let's just check this question over here. With what factor means like double, triple, half, quarter, will the energy emitted change if the speed is doubled 2 times faster? Explain your answer. Okay, so when they say doubled, they don't mean double this one, because then they're going to be doubling. They mean double, they're still talking about this initial doubling. Okay, so they said by what factor will the energy change? So we know that energy is equal to, we could use, for example, let's see which of these would help us. So we could use this one over here. Yeah, because we know that resistance won't change. When you double the speed of rotation, the resistance of your device doesn't change. So we can go fill that in. Now, because they said factor, we don't want to go fill in actual values. We want to fill in factors. Now, you just got to be careful when we talk about the time. Okay, so let's just quickly go talk about this. So we know that the voltage is now going to be doubled, so we put double. Now, we know that the time for one cycle is halving, but this time in the formula is not, it's not the time for one cycle. This is the time that they are talking about. So whether they say 3 minutes or 2 minutes or whatever. So that doesn't actually change. They would say, for example, 3 minutes, and then that would be 3 minutes in this one and 3 minutes in that one. They might say, hey, what is the energy emitted in 4 minutes? So if they said 4 minutes, you would use 4 minutes over here. If they say 2 minutes, you would use 2 minutes. So I know that the time is halving to make one cycle, but this time in the formula is not the time to make one cycle. It's the time that they give you in the question. So that is not going to change. And then resistance is also not going to change. And so we end up with a factor of 2 to the power of 2, which is 4. And so the energy will quadruple. Energy emitted will quadruple. If you're not comfortable with that word, you could say will be 4 times larger than before the changes were made. Here are all the questions we're going to do in this question, but I've split them up so that these 3 are together, and then we'll do that one separately. So this is the photoelectric effect. In summary, you have a metal. That metal has electrons. You then take some type of light, like normal visible light, like red, blue, green, orange, whatever, or ultraviolet. You shine it onto the surface of the metal. If the energy inside the light is large enough, it will be able to cause these electrons to escape from the metal, and then they get released. Okay? Doesn't always happen. The energy in the light has to be strong enough. It has to be larger than the energy in the metal, which is called the work function. Okay, so the first question says, explain the term work function. So the work function, I'll get the definition now, but the work function is the energy that you need to be able to release an electron. It's not the energy of the light. It's the energy that you need to be able to release an electron. It's got nothing to do with this, okay? Now, let's get the proper definition. So here we go. It is the minimum energy that an electron in the metal needs to be emitted from the metal surface. Okay, and then obviously that's just the Afrikaans version over there. So let's carry on. Electrons with kinetic energy of 1.2 times 10 to the minus 9 are emitted from the surface. Okay, so they're telling us the kinetic energy of these electrons when ultraviolet light, which has a frequency, okay, so the ultraviolet light has its own frequency, which is 6.3 times 10 to the 14. Calculate the work function of the metal. You cannot get easier than this. If you understand the basics of the photoelectric effect, this is a plug and play. Like, you literally just plug in the formula. So we know that this chapter is governed by this equation. Okay, so they've given us this. This is the unknown. And so we don't really have the energy of the light, but they have given us the frequency. So then what we do is we use this formula. And we can replace that with that, okay? And so H is a constant on your formula sheet. They've given us the frequency of the light. This is what we're trying to solve, and they've given us that. Come on, that's easy. Okay, so remember that H is on your formula sheet. It's Planck's constant. That's its value. And so we're just going to go fill everything in now. So 6.63 times 10 to the negative 34. And then the frequency that they gave us is 6.3 times 10 to the 14. And then that's going to be equal to the unknown plus the kinetic energy. Sometimes they don't give you the kinetic energy, but they give you the velocity. Then you would just have to go use half mv squared. And then remember, the mass would be the mass of an electron, which is also on your formula sheet. They do give you that. Okay, but in this one, they made it even easier. They literally gave us the kinetic energy. So we're just going to say 1.2 times 10 to the minus 19. And now we just need to solve for W0. And so we end up now with, if you had to go work this out, we end up with, to two decimal places, 2.98 times 10 to the negative 19 joules. Okay, and then this one says, will radiation with a frequency of that be able to emit electrons from the surface? So this is a very easy question as well. We now know that in order to the work function, remember the work function we've just calculated in this previous question, and we know that that is the minimum energy that an electron in the metal needs to be released. So we know that light has to have at least that amount of energy to be able to release an electron. So now they're asking us if they rather use, instead of using UV, if they rather use electromagnetic radiation with this frequency, will that be able to emit electrons? Well, all we need to do, 6 marks. What? That's so easy. Because all we need to do is just go work out. We need to convert this into energy. So we just use this formula again. And that's going to be 6.63 times 10 to the negative 34, which is Planck's constant. And then the frequency of this radiation is 3 times 10 to the 16. And that'll give us 1.989 times 10 to the negative 17 joules. And so now, if you look at this energy here, because it's to the power of negative 17, it means that it's actually a much larger value than this one, which is to the negative 19. This is a much smaller number. So the energy inside the light is larger than the energy of the metal, which is the work function. So will the light have enough energy? Yes. So we can just say yes, the energy of light is greater than the work function. When the photoelectric effect is demonstrated, a negatively charged plate is used. Explain why when ultraviolet is shone on a positively charged plate, no charge is lost by the plate. Jeepers, so this is like going back to grade 10 when we used to use like the basics of electrostatics, even grade 9 where we used to like rub cloths and rulers together and like rabbit fur. We used to do all that nonsense. So it's sort of like, I think, in grade 9 we even start talking about this already. It's not really something we talk about in grade 12. But anyways, let's see what we can do. So what we need to understand is that the way that the photoelectric effect normally works is you shine light, and that light has energy. if the energy is enough, it will cause the electrons to be able to release. However, because we've got it as positively charged, that positive charge is going to hold onto these electrons very strongly, okay? And so it's going to be a lot more difficult for this light to be able to release those electrons, because they are being held by the positive charge, because opposite charges attract. The other option you could also say is that because it's positively charged, there aren't that many electrons, and so because you have so little electrons, it's going to be very you're not going to see a lot of electrons being released. So explain why when you use UV light, no charge is lost. So I think I prefer the option of the electrons being attracted to the positive charge. So I'm going to say no charge is lost, as the energy of the UV light is not enough to cause the electrons to be emitted, as they are being strongly attracted to the positive charge, or to the positive plate.